Okay. Hi. Good morning. My name is Camilo Rodriguez. I'm a researcher here at the Universidad del Desarrollo. I'm also an adjunct researcher to SMI. So, welcome. And I'm just taking 1 minute to do a bit of housekeeping information. Okay. Very important. We are in the building of graduate studies. And first of all, the most important is toilets. I think some of you already found them, but it's important for everyone to know. You go to the left, first one to the left, okay? This room, this floor, we have the same configuration in the next floor, so there is always option, first of all. Second, for those who need to use Wi-Fi, you will find this type of information. So the Wi-Fi is Wi-Fi UDD, and you have there the guest usuario. It's called, it's invitado UDD. You can just pop up and the password. So that's one important information as well. Third information is that all of you must have received a small voucher for meals, for lunch. Lunch will be served in 2 venues. One is just next to us, that is called Mamma Mia, and the other one is Cafe Pretoria, which is just like 50 meters from here. Those who don't have it, yes, this is it. Don't worry, it's not that. We just let us know because we have some of them. Monica, do you have the vouchers? Yeah, Moni has got some vouchers. So those who don't have, important to let us know. Most of you already have it. Yeah? And that's the procedure we're gonna also use for tomorrow. So don't forget to have your voucher. You can fold it into your credentials. It can be folded there. Also very important, we have 2 of our voluntary students here from the university, Miguel and Francisca, for this morning session. So anything that has to do with the venue, questions that you may have about the university, where things are, also about the poster sessions that is going to be held outside in the terrace, where there is already the sports. If you want to know a bit more on how to do it during the lunch break, we can set it up. It's important for you to have them, Miguel and Francisco. Okay? Any housekeeping question? It's just the next room. Yeah. So at 11:55 we split, and the split is just next room.
Someone asked me to mention that a mobile phone was left in the ladies' bathroom. It's upstairs with reception. So
yes. Okay. So yeah. So there is a missing phone that is already in the reception. So normally that's how we proceed. So anything that is been lost, you can always ask at the. Thank you very much. Sorry.
Okay, so we will start with this second plenary. It's my pleasure to present Professor Craig Sheridan from the Leeds University. Professor Craig Sheridan is a chemical engineer, expert in water management and water research, and director of the Water Research and Development Center. His main interests or research lines are the treatment of water and wastewater using wetlands, of course, circular economy, characterization and impacts of acid mine drainage, and he developed a new philosophy or concept called blue is the new black regarding the use of the waters and so on. So today he will present a plenary entitled Coupling the Circular Economy onto an Historic Linear Waste Production Process. So Craig, please, when you wish.
Thank you. Okay, leave the microphone. That's okay with everyone. I'm sure. Can everyone hear me?
Yeah.
Okay, great. Yeah, it's making me more comfortable. I'm a lecturer, so I'm used to speaking loudly. So I'm going to be discussing this concept today. My university's name is the University of the Witwatersrand, which means the University of the Whitewater Ridge. If you can't pronounce it, which almost no one can, just call it Wits University, and then you get it. Okay, so I'm going to start off a little bit. I'm going to speak about mining, its waste, and the impact of that waste on water. So a little bit of the history of my country. I live in a city called Johannesburg. It's now a city of it's a region of about 16 million people. From east to west, it's about 100 kilometers, and the same from north to south. And the history of our city, and in fact our country, is intimately tied to mining. To give you a concept of the extent of this ore body, it was one of the primary reasons behind the Anglo-Boer War, which was a war between Britain and South Africa at the turn of the 20th century. It was important enough for Britain to fight this war that it was the largest number of casualties up until that point, including the Crimea War. So this is a big ore body that we're talking about. In terms of the extent, they've provided it's more than a third of all the gold that you see in the world today from this region, this ore body. So this is a significant ore body, and it extends a couple of 100 kilometers from east to west. At the same time, right now, South Africa is ranked 7th in the world for coal production, and we have a commodities economy in general. So it's a large historic mining country. So we've had significant economic benefit through the extraction of these minerals, but we also experience significant environmental degradation as a consequence of this. So I'm going to have a look at how we mine these products and how we process them. So I've got a diagram. This is a heap leach process. Okay, so this is how you take gold and you take gold ore and you make gold bullion, or as they call it in this graph. And in this graph, we're looking at what typically would be a heap leach process. In South Africa, we tend to not use heap leaching, but it doesn't really matter. The important part in this is that, as you can see, this follows a linear process. So we start with the ore, and we work our way through a large capital-intensive infrastructural footprint, and we reach a final product, which is gold. What's often missing from this diagram is that we don't talk about water. It's implicit in this process, but we never quantify this as a valuable commodity because it's generally doing something else. It's generally transporting gold in aqueous form as a dissolved mineral, or it's transporting slurry in some kind of a form as, it's a conveyance mechanism. It's not a commodity in its own right. We're going to talk about the coal mining process. This is a wonderful diagram from Ethel Smith, a Danish company, and similarly, it's a linear process. So this all over here is actually nothing more than a recycle loop, which is to get your discards back into the process and to optimize your production. Once again, when you talk about this as a process, you're not talking about the water, because it's not what you're trying to solve. You're trying to solve the coal or the gold. So again, it's never valued in a historical engineering conceptual approach. It's just the conveyance mechanism. It's a conveyor belt. So what is the consequence of doing this? And we're really seeing large-scale consequences at the moment. In South Africa, both of our coal and our coal mining ore bodies are very rich in sulfides, especially pyrite. So this is our big challenge, is the pyrite. Our chemistry, I'm assuming most people understand chemistry, but if you don't, it's okay. There are three reactions that acid mine or acid rock drainage follow. The first one is you oxidize your pyrite in the presence of water, and you make a little bit of ferrous iron, a little bit of sulfate, and a little bit of acidity, hydronium acidity. What you then do is you take that ferrous iron, oxidize that to ferric iron, and then you react the ferric iron with the pyrite again. And this is really the problem step, because what you do is you create these 16 hydrogen pluses. And that's the primary acid generating step. And this is, it's a recycling, so it's an autocatalytic reaction. It carries on going, and it just increases and increases. And some of the consequences of this, that we generate these highly acidic, low pH, and I'm separating out acidic and pH. We have a lot of mineral acidity, which is different to hydronium acidity. We create these highly acidic, low pH solutions with enormous potential to mobilize heavy metals. And this is a significant risk to both humans and the environment. Many of the mobilized metals are toxic. We're talking nickel, copper, cadmium, manganese, arsenic, aluminium. And in fact, in Johannesburg, our ore bodies are primarily uraniferous. So we can get up to 70 to 100 milligrams per liter of uranium in this stuff. So that's quite fun to look at. And I don't generally speak about that because I don't have a license to handle uranium or to enrich it. So, but nonetheless, these are toxic metals and semi-metals, etc., etc. And it's costly to treat. And what's really challenging, especially for some of these legacy sites, is it's a never-ending sink of post-mining revenue. And the concept of sovereign wealth funds didn't exist in 1886 when this ore body started to get mined. So we don't have a sovereign wealth fund. Instead, we have quite a developed economy by African standards, but we're paying for it now in environmental degradation instead. If you want to know what it looks like, this is an example of a coal waste rock dump toe seep tailings dam. A coal waste rock dump toe seep tailings dam. Okay, so I have to always say that again. This is quite complicated for me to remember. That has a pH of about 2. It has about 15 grams per liter of sulfate in it, 15 grams per liter, and about 3 grams per liter of iron. Okay. This is not an environmental liability, this is a resource. If you reframe it, and that's this whole concept of black is the new blue. Our waste products are tomorrow's resources, but it just requires that we reframe how we're looking at these things. And that's really what these projects are around. How do we revisualize this as a resource? And actually it's quite easy at 15 grams per liter of sulfate. So what is the circular economy? Most manufacturing processes follow this linear economic model, and there are a couple of things that are like typical of these. They rely on cheap, easily accessible materials. They rely on cheap energy. They normally include planned obsolescence. That's a typical characteristic of a linear production framework. And this is probably most important, is the cost to the environment is externalized. The commons always accept the environmental liability in this linear production framework. This is, and I challenge all mining houses to rethink what they're doing and how they're doing it. Because if we were to pay the true cost, the commons would not be accepting this liability. And, you know, degradation of the commons is a challenge for all of us. It's a challenge here in Chile, as we saw in the previous presentation. So for me, this is a really important point, is how do we incorporate this cost of the environmental degradation into our product, rather than just pushing it out and it's someone else's problem. So what is the circular economy? Well, that's the opposite way, where it's a model of production and consumption, which involves sharing, leasing, etc., etc. We're looking at how do we extend the life cycle of our products, keeping the waste to the absolute minimum. Most importantly is this concept of cradle-to-cradle design. So when we're creating a product, the idea is that when we dispose of the product, that's already been thought of as how is that the resource for the future, for the next generation product. And this ideally creates a long-term value chain. And that's a picture I lifted off the EU website of this is the circular economy. And really what you have is raw materials, you're designing up front for the reuse because it's not about recycling, it's not about it. Production, distribution, consumption, collection, recycling back into this. And ideally with time, this little component gets minimized to nothing. So this is circular economy thinking. But this is entirely at odds with the mining sector as we know it. It's almost disparate. It's a totally different paradigm. So how do we think about putting these together? And that's the question I've been asking is how do we do this? And how can we maybe think about waste and remediation of waste using the circular economy approach? So that's our challenge is figuring out how to couple them. And I believe it can work for the treatment of acid mine or acid rock drainage. And the way to consider an answer is akin to a linear gear mechanism. So I love Lego. That's what a linear gear mechanism is. So if you ever built a Lego car, you'd have a steering wheel which would work with one of these things. Okay. So really what we're saying is, can we use our waste stream to drive a circular economy approach? And I'm going to share a project where we've started to do this. So we had a thing which was called, lots of words, piloting an AMD dam remediation plant using waste products from the steel manufacturing and sugar industries. This was a project funded by our Water Research Commission with some co-funding from a company called Phoenix Slag Services. So what we have is we had an AMD generating site which I shared with you earlier on. We have this coal waste rock dump, and it goes into an AMD storage tank. In an ideal world, you treat that with something like a high-density sludge process where you add a bit of lime. It's a little bit more complicated that, and then you'd have some kind of a polishing step. DSR stands for dissimilatory sulfate reduction. It's a biological processing step. In reality, what's happening at the site is they don't have any of this. So what they do is that's too dangerous to release to the environment, so they pump it back onto the dump. And actually what we have is we have a 15-year heat leach recirculating system. So that's what makes that AMD really interesting. And again, in conventional thinking, what we have is we have a linear process. And every time you touch this, you're going to pay money. So you're going to pay money for lime, you're going to pay money for organic matter for this polishing process, and you're going to generate sludges, which you have to pay to dispose. And this is not great. So we said, okay, so what can we do? So maybe we can replace the lime. And it turns out that because we have quite a large steel industry, a lot of them use a basic oxygen furnace. And what a basic oxygen furnace does is it gets limestone as the flux that you feed into it. And one of the byproducts is this BOF slag. And that's what it looks like. We don't have glacial till. We haven't had glaciers for a very long time. So we talk about gravel. It's typically quarried and crushed material. So it looks like that. And there are lots of things you can do with it. But before you do anything with it, what you need to do is typically irrigate this with water for a few months to rinse out the lime, because it causes all sorts of things in like the construction industry. It has what's called volume instability. So we said, well, lime is what we're looking for, so maybe we can use this instead. And we had a look, and it turns out it's got a very high oxide content. Calcium oxide is approximately 40%. We have quite a lot of silicon oxide. So we said, right, we can actually use that, and it was possible to reuse it. And then we said, well, what about this organic matter? Because paying for ethanol is really expensive, which is the Dutch process, is the Parks process, where you add ethanol into one of these bioreactors and you can remediate sulfate. So we said, what do we have? And just off our escarpment, we have quite a large sugar industry. So we said, well, maybe we can use some of the sugarcane bagasse. So that's a photograph of it. It's the fibrous material that remains after you've pressed out the juice and you've extracted all the blackstrap molasses and everything else. And it also has quite a nice organic content. It's got quite a lot of cellulose, quite a lot of hemicellulose, but it also actually has a lot of residual sugar, which at these very low concentrations are really amenable to these dissimilatory sulfate reducing bacteria to use for their metabolic processes for remediating sulfate. So we said, right, let's do that. And then what we said was, can we design a process around this? So I'm just going to move this a little bit. Be able to. Okay, great. So we said, how would we design this process? So the first step is we install a slag chamber and we start to feed it some startup water. And the reason we feed startup water is you can't put acid onto these alkali substances because they immediately bind with the iron and they precipitate onto this alkaline material. So let's get some slag, pass normal water through it, and we can leach this alkalinity out of the slag. And then we can titrate it with some acid mine drainage. We have a little bit of sedimentation. We pass this residue through our sulfate-reducing bacteria. We can get a treated water tank, and then that can go off. Now this is our treated water. Once we've got this loop starting to work, we can say, well, now we start closing off. We pass some of that back to the slag chamber and feed in new AMD, and then we turn off the startup water. Now what you have is you have a treated water loop circulating to leach out this alkalinity, which you can then titrate with your AMD, and you can come out. And the reason I've called this to somewhere is with this kind of a process, you can dial your outcome for whatever you want. So you might want to use this as a plant water stream, or you might want to treat it to discharge limits. And we've actually been able to get this to discharge. But it's often not necessary because someone wants this water somewhere for something. So when we're remediating these streams, we want to think, what's our end purpose? And in the back of my mind, my younger self always wants to get it to pristine level and put it back into the environment. My older self says, well, someone else actually doesn't need it at that point, and it's really costly to get there. So maybe there's an in-between somewhere. So it's about thinking what's your end use, not just like, let's put it back in the environment. So we did it first in some smaller columns, and then we did it at lab scale. So this is about a 200-liter reactor on a bench top in the laboratory. And at lab scale, we got these kinds of remediation. So for sulfate, we were typically getting 99% for 3 different types. And for the second type, we got 95% removal, 94% removal. This is quite a lot. It's unusually high for one of these high sulfate streams, given that this started off at 15 grams per liter of sulfate. So these are quite good numbers. And then we said, well, what about our metals? And we were also getting fairly high values. Our total removal, for instance, of aluminium was 98%. For all of our different size classes and for the different types of AMD, we tested different types. And for iron, it's also quite high. It's typically at 99%. The one that's not high necessarily is manganese, and that's to do with the pH of the final product. It depends on the pH. But these are quite good values. So we were quite happy with this. So we said, okay, great. Let's design a process because I'm a process engineer. That's my job. So we did that, and that's a typical process engineering language, which is a lot of squiggles and lines. But really, that's what it looks like in reality. So we've got these big tanks. We put them on our site. We've got covers on these things to keep them anaerobic. These biodigesters don't like oxygen very much. They get a little bit titchy, the bugs, when you feed them with oxygen. And it turns out that it's not quite as good at scale. But again, when you're looking at a real process in the field, it's quite different to a laboratory process. We were getting, I would say, quite good values here. We were getting 80% iron removal and 85% sulfate removal on that really horrible AMD, which is 3 grams per liter of iron and 15 grams per liter of sulfate. So we said, that's great, but where to from here? Because we said this is not really, it's approaching circularity, but we're not quite there. We still had sludges to dispose. We weren't happy with this idea. So even though we were offsetting some of the costs and maybe not using raw lime or fresh feed, but we were still not there. So we reassessed the process. And for the same reason that acid mine drainage is really hazardous, that's also really mineral rich. And that was like this epiphanal moment for us, that it contains significant concentrations of rare earth elements and other valuable metals. And many of these are critical. So I think this group here knows a lot about this. They're primarily used in electronics. China is the primary source of supply. The West is a bit touchy about this at the moment, so they're called critical metals. But these numbers are a little bit out of date, but you can see the value that we're looking at. So these are quite large numbers. I wish I had scandium in that, actually. We don't. we have a lot of yttrium and we have a lot of cerium. And a little bit of europium. But what that means is that this system potentially contains hundreds of millions of dollars in rare earth elements. And that's not an exaggeration. When I look at the area of this map and the depth, and I then extrapolate that, because it's not just what we're seeing in this dam, it's also this waste rock dump next door, which has had this 20-year heap leach process on it. This is a legitimate estimate, hundreds of millions of dollars. So we said, okay, well, maybe we can develop a sustainable technology train around this. So we're having a look and we said, well, we start off with high value acid mine drainage. We can apply technologies such as ion exchange, where we can start to pull out these rare earths. We then get a low value AMD. We can then use that. So it turns out that actually the acid is quite useful for hydrolysis of cellulose. That's one of the methods by which we can create biofuels. So not only can we hydrolyze cellulose, we can get an organic residue, and we have actually made glucose, but we've changed this from ethanol. We're actually going more towards biogas because it's a lot easier to handle. So we can use a biodigester over here for this residue. And the idea is that this is our waste product. That's the waste. And if we're reframing it and thinking properly as engineers, that should be our waste product, because it means we're extracting everything efficiently. And that's the challenge for the future, is how do we get everything out? It's not about, oh, well, I got most of the valuable stuff out and we'll stick a little bit in there and let the water go. For me, this is the product that we should be wasting. And that should be pure, because we've done a good job. And that's what we're trying to do with this product. And then ultimately, I ended up with this iron-rich sludge. But the latest research is indicating that that's also quite valuable. We can send that back to the steel mills, but we've also got a really clever guys who looked at some ancient Chinese furnaces, and we can make reductive furnaces and get metallic iron out of this sludge. So there's really interesting research that we can do on this stuff. And then when we step back, we realize that actually these two diagrams are almost the same. And that wasn't on purpose, it was just it happened to be that way. So we realized that actually what we're doing is we're driving circular economy thinking with using of a waste stream into this process. So we then applied for funding, and we got funding for this. We applied to the Dunedin Fellowship Center, which is in Denmark, the Danish International Development Agency, and we have a collaborative project with the Stellenbosch University and the University of Copenhagen. We also have 3 SMEs, so they're very good at ion exchange, they're very good at biodigestion, and they're very good at metallurgical consulting and metallurgical operations. We have quite a nice project where we're calling this assets to value. And we're doing a couple of things with this. So the first is we're trying to quantify AMD, and we're trying to map it at the same time. So if you look at an aerial photograph of many of these commodity areas, you'll see there's lots of red on the aerial photos. So we're starting to say, how can we start using GIS tools, sometimes there's GIS, to map where these sources are. And we're also starting to look at colorimetric methods. Can you do aerial colorimetric analysis on these AMD facilities to get a sense of what's the concentration from satellite photographs? This is quite exciting. This is like really upfront. We don't know the answers to this, but we know we can see it. We're then also looking at community impacts. And this is part of yeah, indigenous is an unusual word in our context because our indigenous people are the San, who are mostly not there anymore. So we're looking at the community impacts, and a lot of these communities in this post-mining landscape are now very, very low-income communities. People don't have work. So if we can generate meaningful work in a post-mining world, this is really useful. But we also at the same time trying to understand what are the ecosystem services that we can supply. So how does this link to, like, what's the value of the water? So at the moment, our society is under quite a lot of stress. We have 16 million people with water resources in my province, with water that's available for about 10 million. So we're starting to see water outages. They call it water shifting. So we have electrical outages for years now. Now we're starting to get the tap switched off for periods every day for the same reason. So suddenly these treated waters have real value for people who don't have access to water. And this is becoming more and more important for us as in a city sort of context. So it's not necessarily rural people somewhere out in the middle of nowhere. It's like modern urban dwellers in an African context. And then we're also looking at composition and quality as well as the potential value. When we start to multiply this across all of our mine sites in South Africa, there could potentially be large-scale resource availability. But not only do that, we have to look at where's our valuable biological feedstock at the same time. So what occurs where? Because if you're transporting the stuff 700 or 800 kilometers by truck, that doesn't make sense anymore. So we have to really design a bespoke process at every single site using this conceptual framework to do this. So obviously our aim, this is great. Our aim is to go from that to that. We don't have rivers typically of this size, but that's the conceptual aim. And how do we do that? Well, it's about thinking about the value. What is the value of this? And it turns out things are the value, like the asset has value. We buy acid for our laboratories. Of course, it's got value. The location, where is it occurring? How do we maximize the value at every given location? What are the metals? Because every case is different, because the geochemistry of every case is different. And then looking at the sulfate, because we've got to have a co-location of organic matter to get rid of the sulfate. And sulfate's one of our killers in this process. Always the sulfate is a problem. Germany, you have quite high sulfate in your water. We have very low sulfates, like naturally, so it's not great for our environment. And really, it's about this interconnection of using technology to drive value through remediating it. So our characteristics are rare earth elements, acidity, iron, other metals, and the sulfate. So some of our preliminary work, I thought since we're a technical audience, I'll try and give you a couple of slides. What's important about this is the iron values. And this has been our challenge throughout, is how can we access these rare earth elements without having every system just swamped by iron? When you're looking at yttrium is 1 part per million, cerium is 6 ppm, and we've got 3 grams per liter of iron. These are orders of magnitude apart. So it's around like, as soon as you start precipitating the iron, you just strip everything out. That's what iron's used for in wastewater treatment works. So we're working really hard on finding these mechanisms by which we can start to not precipitate the iron whilst we're filling out these rare earth elements. And we're in the process of developing the technology train where we're looking at asking the right questions, because if you want a bespoke process, you have to start getting a decision tree. So does, things like, can the AMD be used without prior treatment? Does it contain uranium? These are really important questions for us, not for everyone. For us, they're really important. Does it contain iron? Does it contain rare earths? Does it contain magnesium, aluminum, cobalt, zinc, or manganese? And then is it acidic? And then we work along to, does it contain sulfate? And at each step, we can design a process for remediating that specific compound, whatever that is for whatever location. So yeah, that's really, in conclusion, this global resource, Doug, your presentation is great because it talks directly to this. This global resource scarcity challenge that we're all facing is forcing us to be creative as engineers and as scientists. how do we access these historic wastes? And they really are our potential resources. And, you know, yesterday's millions are tomorrow's treasure troves. So if you're an archaeologist, this is true. And I think the other thing is that circular thinking can be applied to these historic linear processes. It's not always easy to imagine how, but, you know, unless you start, it's not going to happen. And the other one is, there's a lot of funding to do this research. And the trick with that is speak to social scientists as part of your process, because you've got to pull the people into the projects, because it's not good enough to have engineers dictating what happens in society anymore. This is a very 20th century way of thinking. We've got to get people involved. They must understand what we're trying to achieve and try and get that benefit to go down to the people that are really most impacted by these problems. So we're accessing a lot of funding, but all of this has psychologists, it has environmental economists, and it has social scientists who are trying to understand the human element of all of the research. And as engineers, that's always like a little bit challenging sometimes. So yeah, so that's just a list of acknowledgements, not in any order. But to give you a sense, we've graduated probably 12 students on this project so far, and it's still ongoing. So we've got quite a lot of work under the belt, but it's not there yet. So thank you very much.
Thank you, Craig, for this interesting presentation. So we have time for several questions, so okay.
Just shout your question.
Yeah.
We can hear it.
Yeah.
I'm trying to like it. Yeah, I really enjoyed that. So you did mention the challenge of bringing together the sort of waste streams that can be commingled to solve the problem. How likely is that co-location? Is that ultimately that erodes the value or makes it possible?
Yeah, exactly. So it's around understanding what these different organic streams are, because that's typically the missing link in this space. So a lot of our coal mining areas are east of Johannesburg, about 100 kilometers east, and the steel mills are just beyond that. They're about 200 kilometers east. So accessing the steel waste is easy in this instance. The sugarcane bagasse is a lot harder because that comes from Natal, so that's a few hundred kilometers away. But if we had like a co-transport mechanism of like bagasse up, slag down, because slag is also a relatively useful fertilizer for things like sugarcane industries. They can actually use it because of the lime. So we can do that, but we're also looking at sewage sludge as one of our big co-locating mechanisms. And the other thing, that the reason we've got that biodigester there is that if we can access grasses, and I'll explain grasses in a second, we can digest them on site and create our own liquor, carbon-rich liquor for this. So that region, we call it the high veld. It's a temperate grassland plateau. It's extremely productive. Every year it burns, and accessing it is really easy. So you just need like balers to cut the grass. So rather than just burn it and let the ash settle to the ground, we can actually get that in and start generating a bit of biogas. So for us, we're in a unique position. So it's kind of like prairie land in the US, I guess. It's similar kind of terrain. But it is. It's what makes or breaks the process. So it's about looking and knowing what your sources are local. Local knowledge is key. Yeah.
More questions?
Yeah.
You mentioned the rare earth elements. Are those typically associated with coal A and D? Do you find that in coal A and D?
So both, but they typically have always been ignored up until this point because they're at such low concentration in the waste rock. So they've never really been on anyone's radar. But it looks like when we start to assess these different coal waste rock tailings dams that we're actually seeing significant quantities. The goal is slightly different. This region underneath Johannesburg is currently pumping about 300 million liters of acid mine drainage out the ground daily. That's the scale of this problem. And that actually does have rare earths, but again, they're at very low concentration. And currently, they're just liming. So we're looking at, can we access this while it's still in ferric iron form, because that's quite reduced actually as it comes out of the ground.
Would you advocate heat leaching, like this initiating heat leaching to speed up the process?
No. Not necessarily. So I think this is more about where this degradation has occurred. Let's go to those locations and see, because we're seeing this from aerial photographs. You can see these little red things literally all over the place. So it's a case of let's go there and see what's in each of those little sources, and can we then start to set up these circulating loops there. So I'm not sure I would ever advocate that tailings dam is called Kopsia, which means headache in Afrikaans. Kop and Sia means sore, so sore head. Yeah.
How hard is it to get the different companies to work together with their different wastes? When you approach them, are they like open to that, or they know this is what I normally do with my waste?
So you're asking me hard questions. Can we have a technical one? No. So the SMEs are really easy to work with because they're small and they're agile and they're nimble. But we have, it's historically was Anglo coal, it's now called Tungela. Like Anglo divesting in bad mining concepts like coal, it's not great anymore. So they're on board with us and they're part of our advisory board. And they're very interested in this project because they have a lot of these legacy sites, for instance. So they want us to succeed, because what they would ultimately like is to divest of their environmental liability into an SME, a small or medium enterprise that can generate revenue on an ongoing basis to do that. I don't think they're ever going to get that right, but I know that's what they want to do. So for me, if that's what they want to do, let's help them whilst not helping them divest of their environmental liability. So I play both sides of that. But getting access to the other things is hard. Yeah.
Any more question?
If the nuts and bolts, what happens to the hydrogen sulfide produced by your bugs?
We have to capture this.
Okay.
Yeah. So yes, that's toxic. It's very toxic.
Yeah.
So we're not quite there yet at full scale production, but we were trying to process that through a scrubbing system to capture it. Yeah. So if we're really good, we can actually dial it away by keeping the pH a little bit lower and then getting it to precipitate into iron
I
sulfide.
just wonder whether is there some process where you could use it? Maybe not.
People tend to not like it.
No.
Yeah.
Yeah. Thank you. Thank you. Okay, thank you. I invite you to continue this interesting discussion with Craig about this new concept that is very interesting and has a lot of value for the future. So we have now the honor to present Tamara Aravena from the London Foundation. She is a senior manager in I forgot.
So let me very quickly introduce myself. So my name is Tamara Aravena. I'm a engineer, so very much English. I'm based here in Santiago, and I work currently as a senior manager of program design and impact. What I do at the London Foundation, which is a Canadian NGO that belongs to the London Group of companies, all of them within the extractive sector. What I do is that I work with local communities. We try to foster initiatives related to economic diversification. And what I'm going to present you today is something that we have been trying to push forward in recent years, trying to scope business opportunities for the local communities that relies on circular economy approach, right? So what we try to do is to scope where it's possible for us to have something that is profitable, that's going to create revenue jobs for local communities, but but that at the same time is going to be environmentally friendly. So give me 1 second, I'm going to pull up the presentation. It's here. Good, so let me walk you very quickly through the agenda for today's presentation. So I'm not going to dive into the very specific details of the principles within the circular economy model. Professor Craig already provided a very good and detailed overview of this. But we will see like a very broad approach in terms of what we are looking at from the community side, right? Then I would like to show you what are the things that we pay attention at the moment of scoping these business opportunities, and what it is more important in terms of what is feasible from a technical standpoint of view, what we need to secure in terms of these local communities being able to manage these kind of initiatives. And finally, and from a more practical side, I will provide some considerations and recommendations from what we have seen on the ground at the moment working with local people. As Professor Craig already mentioned, within a circular economy approach, the concept of waste doesn't exist, right? What we have is that everything that is for us being seen as an output goes back into the model as an input. So everything goes in. And this is something that is a change in how we usually have in our mind this kind of paradigm in terms of the waste, right? So we see garbage, trash, and we never think about this as something that we need to recycle or reutilize, right? So this is what we try to scope in local communities. And it is not related in this specific case to mining waste, is domestic waste, the one that comes from households, right? One of the things that I think it is important for us at the moment of assessing or scoping these kind of business opportunities is to understand how we can empower local communities and spread the knowledge and the concept that waste doesn't exist, right? That everything that we produce and everything that we use on our daily basis, we are somehow able to reutilize it, right? And I think that is something that we want to leverage and something that we try to change from the very beginning in our mindset. So we try to have a lot of awareness in terms of promoting this as a schools, in environmental workshops that we also try to promote, and so on. So basically, and as we saw in the previous presentation, circular economy is inherently restorative. We have very, very ingrained in this concept of that we need to keep the resources for this to be available for future generations. This is kind of the notion that we have in terms of sustainability, right? And that is also what we try to scope, but from a business standpoint of view. So local communities are able to think on another way or having a different approach for businesses opportunities. I'm not going to stop in all of the benefits that a circular economy model has. You already know more of them, but I would like just to stress this one in terms of technological innovation, because I think it is something that is really important for us to encourage. It doesn't matter of the sector where you work at the moment. I think this is something really important as we try to see how technologies could help us try to recover as much as we can. So now, this is the core of the presentation. I would like to show you what we pay attention to at the moment of trying to foster these kind of initiatives on the ground at the moment working with local communities. So from a technical standpoint of view, one of the things that has been difficult for us, and when working with the local municipalities and the local communities, is trying to have updated data in terms of which is the kind of waste that you have, right? So we will go to the landfill, or we go to waste treatment plants, and we try to understand and have a very accurate characterization of the different type of materials and waste. Also because we need to try to see what would be feasible for us to recover, right? For us to recycle or reuse. So that is the first thing that is important for us to do in terms of assessing if this initiative or the possibilities that we have in terms of recycling, if these is going to be feasible or not, right? The other thing that is important for us to check is if the current, for example, waste treatment plant has all the permits in place. It happens to us that at the moment of trying to dive into the details in terms of how the system is working nowadays, we realize that in some cases they do not have the permits. So we need to try to regularize the situation in order to move forward. And finally, something that is really important for us is that we don't want to create false expectations. We want to be cautious in terms of providing a very robust assessment from the very beginning. So we try to secure that it's going to be enough demand of these recycled products that we are going to be offering as part of this business model. But at the same time, we need to try to estimate the cost. If we are trying to support or leverage this in a community that is very isolated, and we are going to have higher transportation costs for us to sell this produce to a recycling plant in the main city, we need to consider that in order for this business opportunity to be profitable, right? So we also assess that we are going to have good cash flow, a good break-even point, and when that is going to happen, and also all the business model assumptions that we need to bear in mind. Right, so we try to be very, very specific in terms of the economic analysis behind each of these possible solutions. And finally, something that is really important for us is trying to understand that we want to empower the local community for them to own this business, right? So we need to see if they will have the current possibilities in order to address it, and also how we're going to be preparing them, because probably this is something very technical, and maybe they do not have the expertise. We have it unless we are like very expert on the field. So it is a learning curve for sure, but we try to be very close with them in the medium and long term, trying to provide very specific training in terms of recycling processes, standards, access to markets, among others. So I would like to provide some practical considerations and recommendations for what I have seen on the ground from my experience. And one of the things that we have realized is that we kind of have this ideal in our mind in terms of becoming circular, but the current infrastructure and how the system works is on a linear mode. So we need to try to get all the pieces together in order to make this work. And for local communities that in most of the cases do not have access to this, we are the ones trying to support and to get all these different parts together. The other thing that we have seen is the lack of information and disconnect between the parties. In some cases, we are aware of where, for example, the waste is coming, but we don't know, for example, who owns the waste. If it is the municipality, if we are able to use it for other purposes, if we can obtain the organic waste and use it for compost, and if we're going to have some local farmers that will be using this compost, right? So we need to do the whole analysis and secure that this is going to be good, right? Finally, something that I mentioned is the lack of awareness, and it is something that has been gradually changing, right? And also something that is very important is that how we empower them in order for this to change, right? It's something that we have heard from a more technical standpoint of view, but it is important that we try to download this very specific or technical knowledge in something that the community can apply on their daily day. So in some cases, they ask ourselves, well, compost is something that is very easy for us to produce, right? And also to sell, and it's a great opportunity, like for a business case. And in some cases it is, but for more difficult type of waste in order of the treatment, we need to be able to provide that training and that awareness. So finally, something that we have been doing, and we have different programs on the ground based on the different assets that we work with and the local communities surrounding them, is trying to have like a step-by-step guide that enables them to see, okay, if we have to prioritize a pool of initiatives, what we will be assessing, which is the type of criteria that we need to bear in mind. And maybe we are going to have something that is perfect from a technical standpoint of view. It is feasible for us to reutilize or recycle a lot of this waste. But in some cases, we will see that there is not a business case behind that. The costs are higher than the revenue or the profit that we will expect to have. So in that case, we will have a major constraint from economic standpoint. And in other cases, we will see that everything is perfect from an economical standpoint of view and also from the technical one. But we don't have nobody at the local community to lead the project. And in that case, we need to start building those local capabilities, right? So for this, we have created a scorecard. We consider a lot of criteria just to check that everything is going to be robust in terms of the business model that we are going to be supporting. And for the alternative chosen, we carry out a very detailed assessment. And in this one, we try to scope all the material flows in and out, versus the potential of the waste based on volume, quality, and cost. We analyze all the different options in-house and external, also because of the cost as well. And finally, all the considerations that we need to bear in mind at the moment of thinking of how to implement this at site. So that's it. I don't know if you guys have any question, and I'm very sorry if I was too quick on the presentation.
Thank you so much, Tamara. So, as you said, we have time for questions.
Yes, please.
Okay, thank you. So there's this Global Environment Facility Small Grants Program that usually provide funding for community projects. What I envision is our historical economy. But the approach that they use is whereby communities would prepare like concept notes, and then they're submitted for a grant. So I just wanted to know, in terms of the approach that you guys are using, if it's something similar, or what is your intention to ensure that the community has this sort of ownership, you can build capacity, and they can guide the implementation of the project?
It's a very good question. So we have different type of tools and channels. We do provide grants. Also, we have revolving funds in order to support these type of initiatives. But because this is difficult in terms of all the analysis that you need to have from the very beginning, we support them during the process of the concept note. And depending on the amount of the initiative, it could be a concept note or it could be a pre-proposal. And for those cases, we always try to think on what we call an exit strategy. So if, for example, if we don't see that nobody at the local community able to lead the initiative, we will take that lead, but we will work with them on an exit strategy, so we are able at some point to hand it over. So they will be able to continue with it. Sure. Yes.
Yeah, I would like to ask on the aspects of the financial sustainability, whether you have collaboration with any financial organization, banks, or operating banks to assist you with the implementation of it.
That's also a very good question. We try most of the time to work with local partners. But depending on the complexity of the initiative, in some cases we work with international partners, and in order for us to fund this initiative, we usually receive funding from the group, from the lending group of companies. But in some cases, when we see that there is an opportunity for us to apply, for example, for seed capital, that is like any other tool of funding that is coming from the government, we also apply for that. But it's most of the time it's like a hybrid scheme in terms of the funding, and we use a joint venture or a collaboration with implementing partners in order to follow this very close on the ground.
Yeah, thanks, Tamara. The initiatives that you have, are they always in areas of influence of the operations of Lundin? And are there ever any tensions between the sort of communities that are involved in initiatives and the operations? And do the communities sometimes see it as some way to sort of offset what's happening with the operations? And how do you address that?
That's a very good question. I think in some cases, they see it as an opportunity in order to leverage more. Like, for example, if we are scoping the demand, they say, hey, but you, like mining company, you produce a lot of waste. You should be given that as that waste, so we are able to recycle it, and it's like, it is better for the business case. In some cases, because of the mining sector has very strict regulations in terms of how to treat hazardous waste and everything that is coming from the operation, we're not able to use that. But something that is important is that you work with them from the very beginning. We work on the design of the initiative with them. So that is why I mentioned that it is so important for us to start leveraging that knowledge on them, so they are able to see where there are other opportunities for them to do recycling, right? But yeah, I think it is more, they take the chance in order to learn and be more specific in terms of how to do the most of the circular economy within the local community. So.
Are the projects always near a?
Sorry, yes. Most of the time they are nearby the local area of influence of the mining sector. In some cases, we have had some localities that are not nearby, but we see that there is a good opportunity for them, so we support.
Thanks, Tamara. Is there any success story that you can share with us of any of these projects that you have been implementing with the community?
Well, we haven't finished a project that we are working in San Juan in Argentina, and the idea was for us to work with the local government and with the waste treatment plant that they have at the municipality of Iglesia. So what we're doing there is that we already run a very detailed characterization of all the different type of waste that they have. And the business model so far is good. But one of the challenges that we face is that because the local community is not legally formalized as a business, they needed to get together to form a cooperative. So we are in the process for them to do that. But so far, it's looking good. Sure.
Thank you. Great talk. I really enjoyed that. I just finished taking an intro to waste management course for third-year students at Trent University, so I would have loved for my students to see this presentation. It was really great. So you mentioned that you're dealing with small communities and their local waste management issues. I'm reflecting on, in my home province, we're offloading municipal waste management to private management, and we're seeing a change in the way that we define waste boundaries beyond municipalities and thinking more of these areas as waste sheds rather than just within the municipal boundary. And I'm wondering, do you see any examples of that here? Just keeping in mind the economies of scale when you're looking at a mixed waste stream.
That's a very good question, because one of the things that we need to secure, as in any very simple business model, is that we are going to have enough demand over the years in terms of kind of the waste, not the waste, like not the traditional concept of waste, but what we produce as something that we are going to be recycling. And one of the things that we have a struggle is that in some cases you have kind of waste that is private and needs to be treated in some very specific plants. So one of the issues that we had at the beginning is to say, well, who is the legal owner of this waste, right? In the case of the project in San Juan, we realized that it was household domestic waste, so we are able to use it, like the local community owns the waste. But in case, for example, of private sector, and because of there could be like not legal consequences, but you need to worry that there needs to be a specific treatment for like hazardous material or toxic materials. We need to have that very clear traceability in terms of who is the owner and who can use the material in order to be reutilized or retreated. But you mentioned something that is something that we still struggle with in terms of the system. It is still a very linear system. And you have very different parties, like in the case of the private sector, you have a lot of companies that do recycling, but it is not tied in a way that is more comprehensive for the local or domestic household. So we try to leverage that, but like working very close with local communities in order for them to acquire a different business model within this system. But yeah, it is not something that has been integrated in terms of having like a nice hybrid between the private and the public sector. Any other questions? Comments? Thank you very much.
Thank you, Mara. So I will give space now to Jack Evans for words.
So just a quick housekeeping. Before I do, I want to thank our plenary speakers. I think it was an excellent start to the meeting. Several of you will be traveling with us to Puerto Montt on Wednesday. And I think if we talk to some of the Chilean people, they'll probably tell you that the airline that we're flying, JetSmart, is sometimes a little bit unusual. One of the things that you should have each received an email asking you to accept the change of time of the flight. And so could I encourage you to find that email? It might be in your junk folder, it might not. And it's in Spanish, and so you will have to sort your way through it, but there were two boxes, and all I can tell you is the one on the left is the accept, and the one on the right is the reject. Don't hit the reject button. And so we do need each of you to, if you haven't already done it, to go on and accept the change of time. And as you know, we're now flying out at the early hour of 6-something rather than where we're supposed to be. So all you're doing is telling me that you're okay with getting up at 4 or 3 a.m. to get to the airport. So if I could get you to do that, please, as soon as possible, because we're not sure whether we can actually get a boarding pass for you until you actually do accept the change. So thank you.
Okay, so we close now this first plenary session for day one, and now I will give you 5 minutes break for relaxing a little bit, and then before starting the parallel sessions in room B. So thank you very much, and thank you for the speakers so far. Yeah, okay. Sorry. Yeah, just I remember the session of critical metals is in this room, and the other session is titled in the other room. Right? I don't know. Sorry, decision sustainable development in the room 3, right?
Yeah.
Yeah.
I'm Yahaira Arredo. I'm a researcher at SMI in Chile, and I'm going to be the chair for this session. Okay? So, our first presentation is in charge of Albert Graham from Oliver University, and our scientific leader at SMI ICE Chile, Dr. David Rubinos. And the presentation is titled Sustainable Minerals for a Resilient Transition to Net Zero. Un aplauso.
Thank you again. So, I will put in presentation more. Okay, thank you for joining us in this presentation. So I will present just, me and Margaret will present you a brief overview of the upcoming project, Sustainable Mining for Resilient Transition to Net Zero Summit Zero project between the University of Edinburgh, who is leading institution that is leading the project, and SMIS Chile and SMIUQ from the University of Queensland. So, as you probably know, and previous conference remarked, the transition to net zero and the climate change mitigation will create new natural resource and supply chain opportunities, and also dilemmas. So, because the reason is that we will need an enormous amount of new materials to build the new low carbon society. So the World Bank put it that this transition will be by nature mineral intensive. Just without entering into details, to develop this to work this transition, many of the minerals that we need are considered critical raw materials. The term critical, as you know, is not only related with the scarcity in supply, but also with the instability in the supply, and also of geostrategic and political considerations. So there are unexpected increase in demand of, especially for 14 elements, including copper, cobalt, nickel, lithium, and of course, the famous rare elements. Regarding the copper production, as you can see here, that the lithium should be increased. Data from this data from the World Bank are estimations for 2050, almost 1,000% of increase. And regarding the copper, that is also critical, even the expected increase will be lower, is key for the clean energy transition. And it is expected that we need to produce in 25 years all the copper that we're producing, the same amount that was produced in the last 5,000 years. So the challenge is enormous. But from where the metals, these elements come from. So besides the conventional and major supplies like Russia, China, and so on, most of these critical metals comes from developing economies and emerging economies. So, for example, you can see here in Asia, Africa as well, and South America. So the question here is that it's well known that in some of these countries, the regulatory framework is not strong enough to comply with all the regulations. So mining produce or could produce in these countries significant social risk and also severe environmental impacts and social dislocation. So, and what about, which are that meaning impacts? Okay, so As we know, despite the attempts in development and strengthening the regulatory framework and also the corporate management, still there is a severe and legacy of degradation and impacts on communities and also the environment. This has caused, for example, in the form of marginalized communities, illnesses, and also biodiversity damage. For example, as well, it's well known that tailings and main waters might contaminate our water bodies, soils, crops, also contaminating the foods with toxic elements that can reach the body and then poisoning the communities and affecting in a severe manner to the communities and people's health. So here we present an overview of the Chilean mining. As previously mentioned, Chile is the world's largest copper producer with around 50% of the gold production. So what is different regarding or important regarding the copper production is that in comparison with other metals, the copper production generates more wastes as relative amounts. So here in Chile, around 500 megatons of tailings are produced per year, and the accumulated stock is enormous. So these wastes are mainly disposed in tailings surface facilities, and a significant amount of them are not properly managed or are even abandoned. So we need to consider also this particular characteristic of the copper mining in Chile. So in Chile, there was evidences of severe poisoning episodes by potentially toxic metals, like for example lead and arsenic in several populations, especially and particularly in the north. So, in spite of progress regarding the Chilean regulatory framework, still there are several issues that need to be addressed, especially the geochemical stability of copper tailings, the impacts of copper tailings metalliferous leakage on ecosystems and human health communities, and human health communities, and the risk also for exposure to complex mixtures of potentially bioavailable toxic metalloids like arsenic, lead, copper, molybdenum, manganese, nickel, and antimony, especially. This is something that needs to be addressed because it's very rare or never occurs that only one metal is present in the environment. So there are antagonistic and, of course, synergistic effects on that. So it's essential to consider all these elements together. And also there is a need for fit-purpose solutions, not only diagnostics. So we need to develop some holistic and interdisciplinary approaches to solve and to fix this situation. So the Summit Zero Vision, considering the former, is just to create an international network of experts to develop and promote climate and environment smart mining. The aim is to reduce the impacts of mining activities of our environment and, of course, improve the quality of life for the most vulnerable communities, especially. For that, the project will combine expertise from the University of Edinburgh in advanced instrumentation for specification of toxic metalloids in complex matrix, and also experience on remediation strategies and solutions. And this is combined with the SMI's capacity in applied research and transfer of technology and knowledge to the communities, because the communities are finally the receptors of the knowledge that should be done like that. So sometimes we know that it's essential to establish a good link between the science and the final the final receptors of these benefits that are the communities, of course. So the specific scientific objectives of the projects is to understand or gain knowledge on complex, detailed specification of potentially toxic elements. Also the mobilization mechanisms and the pathways of these elements to the human body. And of course the effectiveness of solutions for the rehabilitation and mitigation of such effects in sites affected by polymetallic pollution. I emphasize this of the polymetallic pollution because we consider this essential to reach the goals of the project. The second scientific objective of the project is to develop novel transdisciplinary and integrated methodologies to address a better understanding of the effects of these mixtures of potential toxic elements. And this, of course, will support a better and more accurate ecological and human health risk assessment. And lastly, the final scientific objective of the project is to get robust information about the nanoparticulate, colloidal, and dissolved forms of each contaminant. That it's essential to understand the pathways and also how these metals reach the human body and cause effects. So, as you see, the idea is to combine the geochemistry approach also with some medical geology approach in terms of have a connection between geochemistry solutions and also mitigation of effects on the human body and community. For that, the project considered a study case, supporting the study case, that will be to study the pollution and ecological and human health of a cove in the Atacama coast impacted by a legacy of contamination from copper mining. So the contamination in this area, in the Atacama region, is polluted by several decades by polymetallic contamination from tailings and also spillage from copper concentrate, slags, and so on, and of course drainage from the tailings. And also there is a presence of construction and demolition waste of the channels for transport of tailings and disposal in the sea. So this is a famous area in Chile affected by a legacy of pollution, especially arsenic and antimony, also copper, of course, and probably mercury as well. So here we have the old tailings channel with stars, and these are some photos of possibly copper concentrate or oxidated tailings. So the problem here is complicated because the fishers and local communities use the seafood for commercialization, and so probably there is some presence of arsenic or other metals in the seafood. So it's something that the project will be addressed as well. So this study case, it shows a brief summary of the methodological approach and activities of the project, Summit Zero, that will start with a site inspection together between SMI and University of Edinburgh for sampling soil, water, plants, and seafood. And then in stage 2, we will develop the detailed chemical analysis for these elements and probably some more. And in the University of Edinburgh, we will develop some detailed speciation of PTS with emphasis on arsenic. Finally, all this information will be used together to develop a good, accurate, and precise ecological risk assessment and human health risk assessment as well. And finally, we will deliver risk management and communication plan for the communities. So now, Margaret, we will present you a more detailed overview of the techniques and scientific techniques that we will use within this project. So, Margaret, please.
Thank you very much, and yeah, it's a very great introduction to what we would like to do, and so we really want to work together on this project, and what I would outline just now is very, very quickly It's just the approach we've been building over a number of years. Now, we've not been working in the copper wastes that David was telling you about, but I just want to illustrate the kind of approach that we've taken in building a toolkit of different aspects of direct characterization of solid waste, modelling, and our mineral synthesis to start to understand the wastes, and then that's the first step in the things after that I was talking about, the risk that's posed by some of these and some of the solutions. So this waste that you see here is actually chromium-containing waste. There's about 2.5 million tonnes of this in the city of Glasgow, and it's in areas like parks next to new housing schemes, contaminating surface waters, and also used to be junior football grounds. It's a very complex waste, and so we had to learn a lot in order to characterise and understand why chromium was still a major problem in Glasgow many decades after the chromium industry had actually closed down. So I'm just going to take you through very, very quickly some of the aspects of our work. So some of the more routine aspects would be just using X-ray diffraction, but these are complicated mixtures of minerals. And you have unreacted ores, you have high temperature alteration products because of the industrial process, similar to what Craig was talking about earlier. We have also alteration products and things that come through the industrial process. And then in this case, what we were trying to identify was these very complicated hexavalent chromium-containing minerals, because these were the ones that posed the biggest risk to the environment. And then there's a lot of amorphous material which we're very much unable to characterise. So just to give you a scale, we have these materials about 4% chromium and 1% chromium-6. So these are quite a risk to have in the environment. So it's not enough just to know which minerals you have. The next thing we used was scanning electron microscopy and looking at very thin sections of the minerals after they've been placed in the environment. And that allowed us to look at the inner core, which is the unreacted chromite, and then also the outer surfaces, which are high temperature alteration products. And then within these, that's where we found the hexavalent chromium. So by thin sectioning, we were able to find the key contaminant. And in this case, it was hydrocalamite and hydrogarnet minerals that weren't in databases, but we were able to work out what was there. And this helped us to explain the behaviour we're seeing in the environment, because the hydrogarnet and the hydrocalamite, and you can see here the hydrogarnet, they're inside the waste particles, and it takes time for these to slowly come out of that waste. And explains why we still see images like this even in 2021. That's the centre of Glasgow, next to a new housing scheme. So we use that information about the solid waste characterisation to inform remediation strategies. This is an example of what not to do. So these are the off-the-shelf methods, just using iron 2 to reduce chromium-6. And neither of these work, because iron precipitates almost immediately as iron 3 oxides, and in actual fact, if you use something like iron sulfate, then it actually displaces the chromate from the hydrocalamite structure, and so we actually enhance the release of the chromium into the surface waters. So not really the idea of this, but it gives us a good basis for understanding what will work and what will not work. We back this up with SEM evidence, and the only thing I'm going to show you in this slide is that this is the before treatment, so you've got lots of chromium, and then very little sulphur, and when you treat it with the iron sulfate, you see the sulphur going up and the chromium coming down, so adding to our evidence base using this approach. Then we use that information about the characterization of the solid phase to model what might happen as, for example, rainwater. Glasgow is a very wet city, where it used to be, but it normally is a very wet city, and so we wanted to look at how rainwater might move through these waste materials. And so we were able to use the waste composition information I just showed you in very high pH, these are very alkaline materials, and then to start to look at how the pH might change, but also how the composition may change over time. And by gradually adding in the various solid phases that we identified, we started to get a good match for the experimental data. So you can see our various attempts, we were very good with our initial model at pH 11, but then it took the introduction of a mineral called etrinite to start to get a better picture of what was happening as we came down to pH 10. So this is by adding the rainwater and then looking at how the chromium is released or how it changes over time. And what we found was that hydrogarnet and hydrocalamite dissolve as the pH is lower, but etrinite forms. And so you see a lot of the crystals here of etrinite, these are the ones that are being then represented. And so they not only have sulfate in there, but they can have chromium in that structure. And we found up to 50% substitution with chromate. Etrinite is interesting, we don't know about the stability of it, and so very recently what we've been doing is adding on a new part of our toolkit, and this is involving mineral synthesis. So we've been doing this for chromium, but we've actually also been doing it for arsenic, and David mentioned that arsenic is very important. So this is something that we can develop as we go forward. And so Rebecca Ray and Caroline Kirk, my colleagues in chemistry, they synthesized the C3A phase that you see mentioned here, so calcium carbonate mixed with aluminium oxide, and then they processed that to form the basic minerals that they then reacted with the chromium. And under the high chromium, so it's the high concentration of chromium solution, they formed etrinite as the first product. But what they found then was that over time, then that changed and the more stable product was monochromate. So this might actually identify a bit missing link in our model, so we now go back and really look at our models. But it could also give us the opportunity to look at, if we pass a chromium solution through this synthesized mineral phase, perhaps we can clean up some of the problems that we are currently facing in Glasgow. The waste is underground, it's very hard to identify where it is, and it's actually quite a challenging problem to remediate. And so that's a very whirlwind tour to try and keep on time for our slot today. But what we want is to use that toolkit and to not just use it directly, but to tailor it for the polymetallic wastes that we are hopefully going to visit over the next few months to years. And to use, first of all, the solid phase characterization, and maybe then add on an opportunity that my colleague James Watt will talk more about in his presentation, the diamond light source. I showed you SEM images that we did thin sections through, but this might give us a scope to do this in 3D within the light source with this new dual imaging and diffraction beamline. And this is hopefully going to be used for situations where we have processes that are really unpredictable. We can home in on different parts of the mineral and thin section through that, and also look at processes over time. So it can be a flow-through cell. I think that's something that's quite exciting to be able to trial in this initial project that we have together. And then we take these findings and then use them in the other aspects of the project. I know we're out of time, so I'll stop there. Just thank you very much, and also for the just to acknowledge the funding sources from both of us.
We just have time for one little question, or you can speak with Margaret. Okay.
Really quick question then. How do you choose which kind of seafood to analyze?
Yeah, well, there was a formal study on the seafood by the local communities. So the remaining issue, or not the reply question, is that there was not a specification, not information about the specification. So the level of arsenic were some kind high, but on the presence of other metalloids and metals in the seafood. But as you know, the arsenic forms in the seafood normally considered non-toxic. So it's called fish arsenic, so arsen betaine, arsen choline, and so on. So the question remaining is that the communities were somehow concerning about the presence of these elements found, but there was not any information about the real form of arsenic in the seafood, and also if it will have consequences for the health. So the selection of the seafood will be based on the seafood that are commercialized and taken for the communities to be commercialized in the local markets and so on. So the idea of this project is to reply and to give some light regarding to confirm if there is presence of such contaminants, especially arsenic, as I said, but also chromium, of course, and copper and mercury that is especially dangerous in terms of toxicity in the sediments of the sea because of the methylation by bacteria. So methylated forms of mercury are extremely toxic, as you know. Sample of the famous Minabata Bay episode. So we will look for that, just taking of course, in collaboration with communities, because all the project will be developed in close cooperation with the communities, and then depending on their concerns, we will develop and bring all these powerful tools, instrumentation tools, for giving response, and finally transfer the expectation knowledge to the potential health impacts. This our approach. So we still need to have a look to the exact species that we need to shellfish in general.
Thanks. Yes, an applause, please. Presenter is Camila Carrera. She is a researcher at España Chile, and the presentation is titled Reception and Management of Social Risk generated by mining in the lithium trade.
Buenas tardes a todos y a todas. Esta vez voy a presentar en español. La presentación es sobre la gestión de riesgos sociales y la percepción sobre estos riesgos sociales en el triángulo del litio. Una presentación que hice junto a Nigel White. Somos de SEMAIS Chile, pertenecientes al Sustainable Minerals Institute, cuyo propósito es el desarrollo de conocimiento, de soluciones basadas en conocimiento para enfrentar los desafíos globales de sostenibilidad. Somos un equipo multidisciplinario que trabaja en 4 líneas de investigación: procesamiento, energía, agua y emisiones, desempeño social y gobernanza de recursos, de la que yo soy parte, salud y seguridad integral, y fabricación ambiental y dinámica ecosistémicas. Además, trabajamos transversalmente en 5 programas que les añadió el desarrollo sostenibles. Quería, como con estas imágenes, analizar qué es lo que se les viene a la mente, pero ya hemos hablado muy largamente de esto, así que me lo voy a saltar, porque entendemos que esto puede ser alguna de las consecuencias del cambio climático y la transición energética una de las maneras para enfrentar este desafío. Pero esta transición energética no solamente es un propósito que se han puesto distintas industrias como la minería, sino que distintas automotoras se han puesto el propósito de llegar incluso a la carbono neutralidad en el mediano plazo. Pero para ello necesitamos minerales críticos, tal como se decía en la presentación de la mañana, entre ellos el litio. Gran parte de las concentraciones de las reservas de litio se encuentran en el triángulo de litio: Argentina, Chile y Bolivia. ¿Y qué tienen en común esos territorios, aparte de ser ecosistemas frágiles, como lo mencionábamos en la mañana, que están casi al 100% en territorios indígenas? Entonces nos preguntamos, ¿cuál es la demanda local de esta demanda global? Y partimos analizando cómo se entiende el riesgo social, cuál es su definición. Ha sido ampliamente discutido porque se entendía como un riesgo para el negocio, un riesgo para la industria, un riesgo legal, algo que pone en peligro a la empresa. Pero el ambiental ha empezado a plantear este riesgo como una potencial amenaza percibida por los distintos actores que les pueden afectar. Entonces, el riesgo social como desde la perspectiva de quién experimenta el riesgo. El objetivo de la investigación entonces fue identificar los riesgos sociales percibidos por los diferentes stakeholders que están involucrados en la extracción de litio y explorar cómo estos stakeholders lo gestionan. Nuestra metodología consistió en la extracción de información de fuentes primarias y secundarias, en un análisis cualitativo de la información, la triangulación, la combinación de resultados y gracias a eso llegamos a 3 diferentes resultados. Dentro de la metodología se hicieron 23 entrevistas a actores de la industria, del Estado y de las comunidades de Chile, Argentina y Bolivia. El primer resultado tiene que ver con las categorías de riesgo que se identificaron. El primero, socioambiental. Dentro de los riesgos socioambientales se detectaron específicamente el tema del agua, fue algo que fue muy mencionado, la escasez de agua, pero también la falta de calidad de agua, la disminución de calidad de agua y también la degradación a la biodiversidad. ¿Y por qué esto es socioambiental y no solamente ambiental? Se explica muy bien con el segundo riesgo social, que tiene que ver con los medios de vida y cultura. Las comunidades indígenas suelen tener esta visión en donde se relacionan como dentro de un todo integrado, son uno más dentro del ambiente y sus actividades tradicionales, como por ejemplo la agricultura, están sumamente ligadas al ambiente. Entonces, los riesgos de extracción de litio también tienen que ver con sus medios de vida y cultura y también con el desarrollo de otras potenciales actividades. Por ejemplo, el turismo. No se puede hacer turismo sin agua. El tercer grupo de riesgos es la cohesión social y la participación. Cuando llega un campamento minero o una compañía minera a un lugar, a veces traen con ellos servicios básicos. Pero estos servicios básicos no llegan equitativamente para todos. Hay algunas comunidades que sí pueden acceder a servicios básicos y otras que no. En general se destinan al campamento minero. Se quedan excluidas de estos beneficios y algunas pueden acceder a más beneficios que a otras, lo que también produce un aumento de la tensión entre las comunidades y también entre sus miembros en las decisiones de cómo invertir estos recursos. Otro de los riesgos en esta categoría de cohesión social es la baja de la participación comunitaria en los espacios de toma de decisiones. ¿Quién decide cuánto se les transfiere a las comunidades? ¿Quién decide en qué deben invertir el dinero en las comunidades? Muchas veces las mismas comunidades no son parte de esta discusión. El cuarto es gobernanza y transparencia. Cada vez ha ido aumentando la transparencia de las compañías mineras, vemos más reportes, más indicadores, pero estas bases de conocimiento suelen ser cuestionadas y es que no hay confianza. No basta con tener a disposición informes, demasiada información, el lenguaje que tampoco es tan fácil de entender. Segundo riesgo fue el cuestionamiento de estas bases de conocimiento y también que en cuanto a la gobernanza de esta información empiezan a relevarse los problemas de articulación entre los distintos niveles e instituciones del gobierno. Una comunidad tiene un problema, va a una institución del gobierno y esa institución le dice, no, nosotros no vemos este problema, vaya a hablar con esta otra. Esa otra institución tampoco puede resolver el problema y lo manda a otra institución. Y así al final no se hacen cargo de los problemas y se pueden ver con mayor evidencia esta falta de articulación. Y también la poca claridad de los marcos regulatorios relacionados con el litio. Esto se convierte en un riesgo porque muchas veces no hay claridad sobre cómo avanzar o qué es lo que está permitido hacer o cuáles son los estándares. Y por último, un riesgo que fue detectado por la industria y también por el Estado es un riesgo reputacional y operacional, que tiene que ver con detener la actividad o la producción debido a conflictos o sanciones. El segundo resultado tiene que ver con las acciones y brechas. Este cuadro refleja qué es lo que un actor espera del otro. Entonces, ¿qué se espera de la industria? ¿Qué es lo que las comunidades y el Estado espera de la industria? Mayor transparencia, menor lenguaje técnico, mayor entrenamiento, capacitación técnica, consideración del punto de vista de las comunidades, su cosmovisión, mantener un vínculo estable entre los distintos actores y que se comprometan más allá de lo legal. En cuanto al Estado, se les pide mayor presencia en el territorio, mayor estabilidad, un plan estratégico participativo, mayores presiones a la industria para una mayor compensación a las comunidades, el manejo de conflictos, el trabajo entre los distintos niveles del Estado y también el trabajo con otros sectores. Para las comunidades se les pide mayor apertura al diálogo, más involucramiento, que pidan beneficios razonables y que también se preocupen de mantener este vínculo estable, que se preocupen de mantener esta relación. Y el último resultado tiene que ver con las dinámicas de rebote. Se entiende como una dinámica de rebote cuando un objeto choca contra el otro y cambian de dirección. Entonces aumenta la extracción de litio y se produce un impacto potencial. Aquí voy a dar solamente un ejemplo. Este impacto potencial puede ser mayor escasez hídrica. Y ese es el riesgo que perciben las comunidades en el territorio. Frente a este riesgo, las comunidades deciden tomar acciones, por ejemplo, legales. Esas acciones, que son la respuesta al riesgo, tienen un impacto potencial, que puede ser percibido por la industria, y responden a ese riesgo tomando medidas como, por ejemplo, medidas de mitigación, de compensación, estudios que no habían sido planificados anteriormente, es decir, gastos inesperados que tienen un potencial impacto al final en el negocio. El negocio que fue el que partió toda esta cadena de riesgos e impactos. Y para finalizar, les voy a decir nuestras conclusiones, limitaciones y próximos pasos. Dentro de las conclusiones se encuentran todas las brechas del Estado. Es el actor en el que se detectaron más brechas y más a donde faltó que tuvieran más acciones. También la confianza y la colaboración. No es suficiente con más información, con más informes, con más estándares. Necesitamos confiar en el otro, construir esta confianza para restablecerlas. Luego la complejidad de los riesgos sociales. Un riesgo puede ser percibido por un actor que hace una acción y que se puede convertir en un riesgo para el otro. Puede desencadenarse este círculo vicioso que vimos como en las dinámicas de rebote. Luego, dentro de nuestras limitaciones, fue la falta de entrevistas. Eso lo queremos superar, sobre todo con quienes integran el país de Bolivia, para las siguientes etapas del estudio. Otro aspecto a destacar de la investigación es el proceso de validación. Hicimos un proceso en el que se hicieron talleres, entrevistas, sesiones con académicos expertos en el tema para poder revisar nuestros resultados y poder pulirlos, tener una lista de riesgos sociales más acabada. Luego los impactos acumulativos. No podemos decir que todos los riesgos que detectamos son solo producto de la extracción de litio. Hay impactos acumulativos relacionados al cambio climático, relacionados a la extracción de otros minerales, y para eso es necesario tener una línea base en el momento oportuno para poder ver si las medidas se están atacando realmente a la raíz del problema. También el objetivo más a largo plazo de esta investigación, y algo que encontramos una necesidad, es el desarrollo de herramientas para la gestión de riesgos sociales, que respondan a ciertos indicadores, que puedan medir también, no solo gestionar estos riesgos sociales, que se puedan generar un seguimiento de estos riesgos y que no solamente sea algo como que quede la percepción. Con estos indicadores, con estas bases de datos más acabadas, más pulcras, la idea es influir en las políticas públicas, que se tomen decisiones basadas en el conocimiento y que se genere un sistema de gobernanza de riesgos y también de información más integrado, más participativo y que incluya la visión de las comunidades. Porque la gestión de riesgos no es solamente una medida compensatoria. La gestión de riesgos es un proceso de cambio social. Y como es MIS Chile, estamos comprometidos con el desarrollo de herramientas y metodologías que contribuyan a un mejor manejo de los riesgos sociales de la industria minera. Muchas gracias.
Thanks, Camila. We have time for questions. We are going to translate. Lo voy a hacer en inglés para que so you can understand. But in relation to the interviews, I agree. We have to get more interviews. But how did you select the people or the person you're going to interview? Because you had like 500 other men from the community. So, is there a criteria to say this person is important to interview? Given that we always have trade-offs.
I'll try to answer in English. We select those people from our experience in the territory. We work in Atacama Flat, and we work with the indigenous communities, with different companies, and with different state organizations. That in too. In Argentina and in Bolivia was quite more difficult, and we started in single source articles and in documents of the government, and also with indigenous communities because they talk with each other. The indigenous communities in Chile know indigenous communities in Bolivia, in Argentina, so they identify themselves, for example, as Lican and Thai people, not as Chilean people or Bolivian people. And we also worked with universities, University of Salta, University, I don't remember the name, but with the university we can access to the contact of the relevant actors in the sector.
Another question for Camila? The next presentation is in charge of David. Oh, yes, correct. From the University of Kent. And title, there is another name of the presentation? Yeah.
A little change.
Okay.
Hello everyone. So this is my project on the geochemistry of technology critical elements in Eastern Canada. So on the map here is kind of zoomed out of Eastern Canada around the Great Lakes region here in the bottom. And the study specifically takes place just above Lake Ontario. So for anyone who doesn't know, technology critical elements is a list or a category of elements that changes from one region to the next. Primarily or based on a range of reasons. In Canada, based on an element's importance to economic security. If the element has a threatened supply chain, if they're required for transitioning to a low carbon economy, and for a range of development, primarily military and industrial. So Canada's critical element list includes the rare elements, which are highlighted in red, the platinum group elements highlighted in blue, and various other assorted elements highlighted in yellow. The objectives of this research are to investigate the influence of different geologic backgrounds with distinct weathering rates and varying critical element content on the characteristics that govern critical elements, the environmental processes governing the geochemistry of critical elements, the seasonal variations in the sources and cycling trends of critical elements over time, and any differences in anthropogenic emission and natural geochemical processes. So just again, this is where the study takes place, but we can zoom in on this and add a little more detail to the map. So highlighted in red in the top section is where the Canadian Shield is, and just below that in the lighter green is the Great Lakes or St. Lawrence lowlands, which are two different geologic backgrounds. And the four or so dashed black lines outline the watersheds of the three rivers that the study takes place on. So the first two are the Trent and Otonabee rivers, which are part of a continuous system that's separated by a rice lake in the middle. This watershed is almost split exactly in the middle, with half of it being on the Canadian Shield and the other half being in the Great Lakes lowlands. Our third river is the Ottawa River. Crosses three different watersheds, but the majority of them are all located on the Canadian Shield. We collected water samples from the entire length of the Otonabee and Trent River, but because of the significant larger length of the Ottawa River, we only sampled the section that follows the border of the Canadian Shield. So for anyone who's not familiar with the area, probably wondering why or what the importance is of the Canadian Shield and Great Lakes lowland. So the Canadian Shield is represented by the Ottawa River, and it has a geologic background of primarily Precambrian and igneous metamorphic rocks. So we have things like aluminosilicates and granite. And kind of their key features, they're highly resistant to weathering and erosion. So the background image is one of the sampling sites on the Ottawa River. And it has lots of little islands like this in the background that have very thin layers of soil, and they're primarily made up of exposed rock that looks like these. Our Trent and Otonabee River represent the off-shield or transition to off-shield. They have a geologic background primarily of Proterozoic and sedimentary rocks. So this includes things like carbonates, calcite, limestone, and dolomite. And compared to the Canadian Shield, these rocks are highly susceptible to weathering and erosion. So this background image was taken from the Otonabee River. And as you can see from the river shoreline here, there's a lot of erosion that's taking place. And it has a lot more rocks that look a little more sandy like this. So samples were taken from each of the four seasons on all three rivers, except for the Ottawa River for the winter season, which is going to be done shortly after we return from this conference. We had some delays in waiting for a new ICP-MS to be installed. So for this presentation, we just have some preliminary data that was collected for the winter seasons on the Otonabee and Trent River, which is the ones highlighted in yellow. So first we can plot the conductivity measured on these rivers to the ratio of sodium plus sodium and calcium on a Gibbs diagram to get an idea of what the major source of ions are in these two rivers. From this we can see that all of our points lie in the middle towards the left half, which tells us that rock weathering is the main source of ions on both of these rivers. And you can see that the Trent River, which is below the Otonabee, points have a slightly higher conductivity, which is showing the transition farther away from the Canadian Shield. There's also one point that's way off on its own, and the reason we see that shift is because this sample was collected just below a wastewater treatment plant on the Otonabee River, and the sodium concentration here was measured about 5 times the average of all other samples. Since we know rock weathering is the major source of ions, we can also look at what type of rocks are being weathered. So this can be evaporites, silicates, or carbonates. And a river draining a carbonate-only background, which would be our Great Lakes lowlands, You'd expect ratios of calcium, magnesium, and carbonate to sodium around 50, 10, and 120, which puts you up in the top right corner. But for silicates only, which is our on-shield, you'd expect much lower ratios, about 0.6, 0.2, and 2. All of our samples lie in the middle of this graph, a little closer to the silicates, which shows us that there's a mixing of both weathering products, which is to be expected as the watershed is half on and off the Canadian Shield. If you zoom in on these points, you can see a little more clear that there is the transition from the autonomy in orange to the Trent River in blue as we move farther off the Canadian Shield. And again, we have 1 point off on zone from the wastewater treatment plant. We can also look at the ratio of magnesium and calcium, which are two major components of a lot of the rocks found in this background. So as you move from a 1-to-1 ratio to 1-to-2 to a 1-to-3 ratio, which are represented by the blue, yellow, and green lines, you would expect to see decreasing weathering of dolomite and increasing weathering of limestone. So you can see all of our points lie below the 1-to-3 ratio. So we expect very low contributions from dolomite weathering and very high contributions of limestone. You can also look at inorganic carbon and calcium with a 1-to-1 ratio and 2-to-1 ratio, showing moving from 1-to-1 to a 2-to-1, increasing contributions of carbonate weathering, which would be from the off-shield region. And again, from this one, you can see our points lie between the two, but from the Autonomy River in orange to the Trent River, there's an increase in the slope, which shows the increase of carbonate weathering. And this is just to show again that this is kind of what we would expect to see. Both of the rivers, even though they lie entirely in the off-shield portion, there's still some influence from the Canadian Shield background, but it decreases as you move downstream. We also have some more measurements for conductivity for more of the seasons. So this is the spring, fall, summer, and winter conductivity for the Autonomy and Trent. The Autonomy River is represented by the blue background, and the Trent River by the purple background, which is separated by Rice Lake, is the red background in between. You can see as you move farther off-shield on the Autonomy River, there's a steady increase in conductivity, but this kind of stabilizes afterwards along the Trent River. We also have some of our conductivity measurements for the Ottawa River, which follows a steady increasing trend. Even though the majority of the watershed is on shield, it's probably due to it bordering. Same with inorganic carbon, which kind of represents our carbonate weathering. You see the same trends on both of the rivers. Lastly, we can look at one of our critical elements, gadolinium. It's a rare element that's used in medical contrast agents. Because it's used in medicine, it's designed to pass through the body, which means it also ends up in our wastewater treatment plants, making it an excellent indicator of medical-related rare earth element contamination. So you can see after the wastewater treatment plant on the Autonomy River, which is represented by the vertical red dotted line, looks like there's a jump in the concentration of gadolinium, which indicates there might be some contamination there. But we don't see any jump after the wastewater treatment plant on the Trent River, likely due to the smaller community size and smaller hospital size. But you might notice it follows the same trend as conductivity and inorganic carbon. There's a steady increase along the Autonomy River, which stabilizes along the Trent River. But but these concentrations alone normally aren't enough to say that there is contamination occurring. So by normalizing these values and trying to calculate gadolinium anomalies, we can look at some values that are generally agreed upon. So above a ratio of 1.4 to 1.8, you'd expect anthropogenic contamination to be occurring. And only 2 of our points pass the top end of this ratio, just below the wastewater treatment plant and the landfill on the Autonomy River, but none of the points on the Trent River pass this line. Because all of the other points lie along the 1.4 line, it suggests this is just because of the increased weathering of the offshore region. So the next steps for this research are to complete our sampling on the Ottawa River and the elemental analysis for the remaining seasons and see how these trends compare throughout the seasons, if there's any variations, and try and determine why those are happening. And lastly, I'd just like to acknowledge and thank my supervisor, Dr. Guidang, and the Enigma Lab, as well as the IES for this opportunity and their travel support.
Question from the others?
Very complicated. The sampling along the river, are you sampling those at tributaries? And if not, have you considered sampling the tributaries and sort of looking at signals of sub-watersheds that might give you more resolution? Because right now, when you measure the main river, it's obviously covering a huge area.
So I haven't taken any samples of any of the tributaries, but I have them above and below, so we can try and determine if there's any influence from them. I didn't mark them on these graphs, just because it's a little confusing when there's too many vertical lines, but I do have the location of all the tributaries along each of the 3 rivers. And so far, it doesn't really look like there's much of an influence through from any of them, especially on the Autonomy and Trent. The other rivers flowing into them all come from the same area, so they kind of follow the same trend moving down.
Another question?
Yeah, so did you conclude that the wastewater treatment plant is a contaminant source? And so where do you think that's coming from? What would be the source of the gadolinium?
Yeah, so as far as I can tell from normalizing those, and because the anomaly is so high, we're pretty confident that it is from anthropogenic contamination, which would be from medical contrast agents at the Peterborough Hospital.
Yeah, I can just shout it quickly, and again, it's a follow-up to Ian's question. So if the signal doesn't come from the tributaries, where does it come from?
Sorry, well, which signal are you?
I mean, if you're looking at concentrations and mixing, I mean, is it just a natural geological background? You don't see a change above and below tributaries?
Yeah, from everything I've seen so far, it's just based on the natural geologic background and how easily or not that they weather.
I have a follow-up question. I can see for the lowlands, the geology might be pretty similar in limestone over large areas, but for the Canadian Shield, the geology is quite complex. You could be changing rock types from 100 kilometers down the road. So it might be worth thinking about that.
Yeah, looking at the geologic maps, there is a very large variation in what kind of minerals are there, but in general, all of them have pretty low rates of weathering. So the rate of contribution of critical elements to the river is pretty low.
Thank you. And the last presentation is in charge of Ashley Granahan, from the University of Trent.
All right, hello everyone, my name is Ashlyn. I'm a master's student at Trent University. Today I'll be discussing with you one of my results chapters. I'm investigating whether we can determine the uptake mechanisms of rare earth elements within aquatic organisms in the background conditions in order to provide some insights on environmental risks before we expose these aquatic organisms to high levels of rare earth elements. So just to begin, I'm going to define what rare earth elements are and their importance to the global economy and my project specifically. So rare earth elements, they are composed of the lanthanide series from lanthanum to lutetium, as well as non-lanthanides, scandium and yttrium. This group of metals are uniquely different from the rest of the periodic table because they hold very similar physical and chemical properties, such as all holding trivalent charge. It's not tightly defined, but they can also be split up into light, medium, and heavy groups based on their ionic radius and based on their chemical behaviors in an aquatic environment. So this group of metals have been defined as critical minerals around the world. Their demand has increased as we continue to integrate them into the high-end technology sector. We find them in places like our computers, our phones, electric vehicles, along with military and medical equipment. These group of metals help increase our economy, improve human livelihood, and advance technologies. So, in order to meet this demand, there has been a global push to increase the extraction of rare earth elements. This is just an animation to show you what's currently happening around the globe. We have a lot of mining sites and processing facilities opening up in order to extract these elements. And as we increase the extraction, there is potential for the release of rare earth elements into the surrounding aquatic systems and terrestrial lands. There's actually been found in China that there is really high concentrations of rare earth elements in croplands specifically and the lakes surrounding their mining sites. This puts a lot of pressure on the communities that live around these sites because they rely on clean drinking water and clean land to grow their crops. So it's really important that we start looking into the environmental risks that could be put on the aquatic ecosystems and humans themselves. Because we don't even have any regulations on the release of rare earth elements currently around the globe. So, however, before we look into environmental risks, it's really important that we take a step back and just determine the natural uptake mechanisms of rare earth elements in an aquatic system, because these background levels will provide us knowledge on how they transfer throughout an aquatic food web. If when rare earth elements are exposed into an aquatic ecosystem, could they even be susceptible to getting into the organisms that are living there? So what I have done is created a lab-based mesocosm experiment looking at the background conditions of the rare earth elements. I exposed a number of aquatic organisms at different levels of the food chain to the aqueous environment, which acts as a dissolved form of rare earth elements, and their food, which is acting as a particulate form, to determine if these rare earth elements can be uptaken, again, through the particulate or the dissolved form. I'm hoping this preliminary information can provide us more insight on a natural ecosystem when these organisms living in lakes that are being exposed to higher levels of rare earth elements, if they're susceptible to uptaking from these exposure routes, the dissolved and particulate form. So to complete this background mesocosm conditions, I cultured and collected organisms such as Euglena, Daphnia, crayfish, clams, mussel, and minnow. I exposed them for 60 days to the Autonomy River water outside of Trent University that's acting as a dissolved form. And then I gave them food acting as a particulate form, again to determine can these organisms even get these rare earth elements into their body and in what form. This is a summary of the organisms and their exposure routes. So they were all exposed to Autonomy River and then given different food types based on their nutritional needs. After this mesocosm experiment was completed, I prepared the samples for multi-elemental analysis on the ICP-MS at the Trent Water Quality Center, just to determine the composition of these rare earth elements inside the aquatic organisms' tissues. Well, my figure 1 here is just showing the natural lanthanum background concentrations within the test subjects and their food and water exposure. The test subjects are found on the left-hand side. You can see naturally lanthanum concentrations are highest in the soft tissue of the gastropod and mussel, right here. When you compare these concentrations to their food exposure, which were the spolina pattern and chickpea pattern, the concentrations are a lot higher. This provides some insights that these organisms are bioactively uptaking and pumping these lanthanum from their food into their body, causing some potential bioaccumulation effects. Comparably, you see the minnow, the soft tissue, is in purple. The lanthanum concentrations are the lowest. If you compare this to the food that they've been eating, their concentrations are a lot lower. This is showing some deprivation processes. The minnow is taking the lanthanum out of their body. So just comparing the natural concentrations of the aquatic organisms and their food and water exposure provides us some bioaccumulation potential insights, but it doesn't directly show us whether they're uptaking rare earth elements through these forms. So in order to pinpoint the uptake mechanisms of the dissolved and particulate form, I chose to use rare earth element fractionations. I bioplotted them to compare the enrichment of light, medium, and heavy groups within the aquatic organisms. These fractionation signatures were then compared to their food and water exposure. So let me just try to explain. Firstly, a fractionation is just a ratio between, again, light, medium, and heavy rare earth elements to show which group is more enriched in the aquatic organism. And once we figure out what group is most enriched, we can compare that fractionation of their signature, of their exposure form, which the X's are representing the food, and the circle is the dissolved form, the autonomy river water. And if those signatures overlap each other, this is showing direct indication that the aquatic organisms are uptaking the rare earth elements. So just to explain the graph, the x-axis here is comparing fractionation between heavy and light, and the y-axis is showing medium and light. So a fractionation of 1, which is this gray bar, this means that there's no enrichment of one group to the other. But if you have a fractionation higher than 1, for example, on the x-axis, fractionation higher 1 shows erbium is the more enriched group of rare earth elements. This is a heavy rare earth. So again, I'm using fractionation signatures to determine could these aquatic organisms be uptaking the particulate or the dissolved form. And what I've found, there seems to be a division. So if you, pelagic organisms that you find like floating in lakes and water, they're represented by the purple shapes are minnow, and their different organ and tissue types. The light blue is Daphnia, and the light green is Euglena. So they're all enriched in erbium, the heavy rare earth element. Their fractionation signature is very similar to the autonomy river fractionation, which you can see right there. This is showing, again, that they're uptaking from the dissolved rare earth element form. But when you compare to benthic organisms found at the bottom of ecosystems, for instance, the brown shapes are crayfish. Their fractionations overlap with their food, and the autonomy river is showing they're uptaking from both forms. But gastropods, which are the red soft tissue, they're uptaking from their spolina powder exposure, showing that benthic organisms can uptake from both dissolved and particulate, depending on the organism. Lastly, this figure is just some preliminary results that I am currently trying to interpret. Cerium anomaly, I'm using cerium anomalies and looking at them in the aquatic organism tissues and comparing their food and water exposure to try to use as a tool to trace some biogeochemical transformations within the cell of the aquatic organisms after being exposed to their food and water exposures. So let me try to explain. Firstly, a cerium anomaly is just showing the behavior of cerium compared to their neighboring rare earth elements, which are lanthanum and paradisium. Cerium anomaly of 1 just indicates that the behavior of cerium is the same compared to lanthanum and paradisium. A cerium anomaly higher than 1 shows the enrichment of cerium, and an anomaly that's less than 1 shows a depletion of cerium in the organisms. So right now, we see a depletion of cerium within the soft tissue of mussel, minnow, Daphnia, and Euglena compared to their exposure routes, which are the X's and the autonomy river. This might be due to some transformations of cerium being oxidized to cerium 4+, where there's a different trend occurring in crayfish. We have an enrichment of cerium. Now, this could be due to the reduction of cerium into cerium 3+, but there's studies showing that their hard shell in other areas of the St. Lawrence River also has positive cerium anomalies. Just to summarize, this is again a new topic that I'm investigating, and we're not sure how these biogeochemical transformations affect uptake mechanisms right now. So just to summarize, we were able to look at the bioaccumulation potential in benthics. We could use rare earth fractionations to determine that these aquatic organisms are uptaking rare earth elements through the dissolved form, and benthic organisms are uptaking through the particulate and the dissolved form. So essentially, in a real-world ecosystem, when these organisms are exposed to high levels of rare earth elements around these mining sites, pelagic organisms are more susceptible to uptaking the dissolved form of rare earth elements, and benthic organisms are susceptible to uptaking the dissolved form through the water and the benthic through the food or the sediment that they're exposed to. But these background conditions in the lab need to be validated with real-world ecosystem fractionations to see if the same transfer mechanisms are occurring. Again, to validate that aquatic organisms are susceptible to uptaking rare earth elements through these exposure routes. And once this has occurred, we can then suggest certain organisms that could be used as biomonitoring tools to just assess the health of the ecosystems and lakes around these mining sites to keep them a bit more safer from the pollutants. I want to say a big thank you to everyone here and listening to my presentation, to IIES, and my colleagues and supervisor. You've been a huge support through my project, and I'd like to take any questions now.
For a couple of questions.
Okay. Can you do anything on the rate of the uptake? Like how quickly those organisms will uptake it when they're exposed to it? Like if there's a flash flood and suddenly more gets released into the river, that sort of thing?
No, we did not look at the rate of uptake from our project. We were just seeing primarily like if they're able to uptake them or not, firstly.
I have a follow-up question. I mean, after the uptake, do they continue? I mean, is it a linear increase, or they plateau, or they leach, for example? Do they lose it over time?
That's a good question. Yeah. So the organisms like Daphnia and they're able to deprivate what they're being exposed to. So over time, like their concentrations are getting lower. With the benthic organisms over time, they're not. Yeah. Does that answer your question?
Perfect. Okay, it does sound like the benthic then are better indicators.
Yes. Yes.
Another question? Yes. Thank you, everyone. Thank you.
Well, this is you.
¿Saben cuál es la reserva? Pregunta, ¿cómo se hace? Porque yo he visto en las salas.
Sí.
La derecha.
Parece que es la derecha.
Que dice que es la otra sala. Va a preguntar como quién es. Ya, así que están listos antes que nada.
Ok, ya. Primera pregunta.
Voy a comprar más allá.
Ya.
¿Te espero?
Y después de la pregunta, se podría.
Sí, sí. Vamos a decir. Resultados de la tesis de magíster y de mis profesores están. Capítulo.
Sí, ya.
I think I'm chairing. It's good to get rolling.
I'm gonna put yours on.
Yes.
And then we'll send you to a trip down. I don't know.
I just want to check.
Yeah, do your thing.
Right.
We talk about Larry?
Full screen. All right, good afternoon, everyone. Thank you to the organizers for this session. So I'm going to talk to you about CO2 sequestration within tailings from nickel mines. We've heard a lot about this morning. Nickel is a critical mineral. Its main use today is in stainless steel. And like other critical minerals, its demand is supposed to double by 2040. And that really, as previous presenters mentioned, is a big challenge for the mining industry. Many of the high-grade ore deposits have been mined already, so we need to rely on lower-grade deposits, which means you're generating more mine waste, more greenhouse gas emissions. So you can mine nickel from a variety of ore deposits. I'm going to talk to you about serpentinites. Serpentinites form through serpentinization. So as an example, you can take forsterite, which is a magnesium silicate, undergo hydrothermal alteration or serpentinization, form serpentine, very important brucite, Margaret had in her slide, awesome mineral for carbon sequestration, and then accessory minerals like magnetite and aurorite, nickel iron alloy that you can mine for nickel, or other nickel-bearing minerals like pentlandite, which is an iron nickel sulfide. The reason why brucite is so valuable for carbon sequestration is that it has a dissolution rate that is 2 to 4 orders of magnitude faster than the magnesium silicates like forsterite and serpentine. And so it's very reactive with CO2. So thinking about carbonation, we need a source of these minerals. These can come from mine tailings. Mine tailings are the waste product from ore processing. They're very fine grained, more reactive because of their surface areas. So they can supply cations like magnesium, they can buffer pH, and then you need a source of CO2. That could be from the atmosphere, or maybe a point source of CO2, or some other source. And then ideally you're forming, in this case, magnesium carbonate minerals, and that is your sink for CO2. And any one of these can be rate limiting to the overall carbonation process. So that's a bit of background. So first I'm going to take you to the Batiste deposit in British Columbia, Canada, and we'll look to see what is the potential to sequester CO2 at this deposit. And then we'll go to Australia, to the Mount Keith nickel mine, and we'll look to see how much CO2 is being sequestered under traditional mining practices, and what limits carbonation. And then I'll show you some experimental and modeling studies where we aim to accelerate brucite carbonation to sequester more CO2. So the Batiste deposit, it's very large, also very low grade. There's the potential to mine that aurorite, the nickel iron alloy. Again, it's also a brucite bearing serpentinite. This is kind of what the ore looks like. It's mainly composed of serpentine, again, magnesium silicate, but it does have minor abundances of brucite and magnesium hydroxide. And the mineralogy is critical because it dictates both the capacity to sequester CO2 as well as how fast or the reactivity of the rock. So one tool that we use for assessing mineralogy is quantitative X-ray diffraction. It's a very useful tool. So in this example from the Batiste deposit, 95% of the rock is serpentine. That is the bulk of the capacity to sequester CO2. But serpentine being a silicate mineral, it's very recalcitrant. And then it has about 1% brucite. You can think of that as the low-hanging fruit. It's very reactive. So much of the reactivity of the rock lies with the brucite. So colleagues of mine, Vanderzee et al., they had access to all the cores for the Batiste deposit. And so a huge geochemical database. And they were able to translate the geochemical data to mineralogical data. And they calculated what they refer to as the labile magnesium component, which is mostly brucite. And so what this graph here is showing is the percentage of core length versus the calculated labile magnesium, again, mostly brucite. So you would need about 1.3% labile magnesium to offset the truck emissions for this prospective mine. The deposit has about, on average, 2.3%. And then if you want to offset truck emissions and natural gas emissions from to power the mine, you need about 3.9%. Now, this mine being located in central BC, it might actually run on hydroelectric, so its emissions could be less. The bottom line is, within this space, there's enough labile or reactive components, the low-hanging fruit, for the potential or possibility of carbon neutral mining. So in some experiments, I looked at determining the carbonation rate under traditional mining practices. That's what's shown on the left here. And extrapolating my rates to the 5 square kilometer proposed tailings impoundments, it would sequester about 17,500 tons of CO2 per year, which is a lot less than what you need for a carbon neutral mine. And this is because not all that brucite would react under traditional mining practices. So point being is there is the potential for a carbon neutral mine, but not using traditional practices. So let's go to Australia, Mount Keith nickel mine. Again, it's also very low grade, only about 0.6% nickel. They process a lot of ore, about 11 million tons per year. They emit about 370,000 tons of CO2 equivalent per year. Again, it's a brucite bearing serpentinite, so much of the capacity to sequester CO2 is within the serpentine. It could offset, in theory, 900% of their emissions. But even the brucite, which is on average 2.5%, could offset about 60% of their emissions, maybe even actually more than that. These photographs don't really do it justice, but the tailings impoundment is huge. Almost 17 square kilometers. And it has a number of towers, like the one shown here, and the towers spew out tailings slurry. And the tailings are wet, they're very fine grained, again, they have that reactive brucite, and they're just soaking up CO2. And so you have this sort of giant pancake that keeps getting bigger and bigger over time. And what you see at the mine sites are these white crusts, and they contain a mineral called hydromagnetite. Again, that's your sink for CO2. It's nice and stable, it's benign. So a colleague of mine, Sasha Wilson, and I sampled Mount Keith's nickel mine quite extensively. Sasha did quantitative XRD to quantify the amount of hydromagnetite, that's the sink for CO2. And he also found that there was a fair amount of unreacted brucite. It works out to be about 40,000 tons of CO2 per year, which is 11% of the mine's emissions. And again, that's being done accidentally. It's at zero cost because they're not doing anything to speed up the process. If you ignore that Mount Keith is a mine, it would actually be one of the largest CO2 mineralization demonstration projects in the world. What limits carbonation? Well, what Sasha found was by looking at the stable carbon isotopes, of the carbonate minerals, they are out of equilibrium with atmospheric CO2. And a number of follow-up experiments also showed that brucite carbonation is limited by the supply of CO2. So if you want to achieve greater carbonation, get more complete reaction of brucite, you need to supply more CO2. So I'll show you some laboratory and modeling experiments that aim to try and accelerate brucite. So one was through modified tailings deposition, the other being aerating the tailings, and then lastly using some alternative source of CO2, possibly in this case waste organics. But the whole idea is to target that rate limitation. So going back to Mount Keith, I mentioned that there was this unreactive brucite at depth. And that's because the tailings are deposited, they're reacting with atmospheric CO2, and then more tailings come along, bury the old tailings, isolate them from the atmosphere, and that kind of stops the reaction. So my colleague Anna Harrison used reactive transport code Min3P to model different deposition rates.
That's what's being shown in this graph here. Roof site remaining versus exposure time. At Mount Keith, they deposit about 50 centimeters on average of tailings across that 17 square kilometers. If you were able to have a larger impoundment or make better use of the current impoundment, have thinner flows, you would increase the exposure time and get more efficient roof site carbonation. So just by modifying tailings management, you can sequester more CO2. Going back to the Petit deposit, I showed this graph before. The blue line is my experiment. Again, this is sort of traditional mining practices to determine the carbonation rate. Anna also looked at doing modeling for these experiments. The green line is if you could keep the tailings in equilibrium with atmospheric CO2, which could possibly be done through sort of aerating the tailings. Again, keep in mind these are alkaline tailings, low sulfur. So we're not generating acid. But you can speed up the rate by 5 times, again, achieving more roof site carbonation. And then another way would be to instead supply higher concentrations of CO2. Some of the previous work that I did was also looking at using CO2 from point sources. So Mount Keith, they burn diesel, and so they do have point sources of CO2. My student, Justin Lockhart, looked at the possibility of using waste organics, kind of a remediation scenario. And he found that he was able to accelerate the rate of carbonation by about 10 times compared to the aeration rate. And so he got 102 kilograms CO2 per ton tailings per year, compared to, let's say, the Mount Keith rate, traditional mining practices of 3.6 kilograms CO2 per ton tailings per year. So again, trying to speed up roof site carbonation, achieve all that potential for that labile component, and there's the potential for a carbon neutral mine. This is my last slide here. You might be wondering about other deposits. So I just highlight this paper by Bullock et al. They looked at magnesium-rich alkaline mine waste from metal mines as well as diamond mines. And the basic idea is that mine tailings are generated on hundreds, if not hundreds of millions of tons of rock per year, or even gigatons, and there's gigatons upon gigatons of historic mine waste as well. My colleagues and I just finished up a project with De Beers in South Africa and Botswana, where we looked at the potential of CO2 sequestration in those mine wastes. They're not as good as the brucite variants or pentalates, but still quite good. And then right now, we just started a project with Tech Resources. Tech does have mines here in Chile. And the idea is to look at mine waste from what we call unconventional ore deposits, looking for different carbonation pathways that might be used. And that's all I have. If you have any questions, again, thank you for your time.
Presentation, Ian, and we do have some time for some questions. Anybody other than Julian? Julian.
I'd like to follow on from my question. You mentioned that, of course, you can increase the rates, but do they ever get saturated? Like, is there ever a mine waste? Is there a potential that mine waste just becomes CO2 saturated?
I suppose not until all the brucite's consumed. I suppose pore water could become saturated, yes. But then I guess the dissolution of the silicates would take over to some extent, but the reaction rates would be slower.
And is there a potential? It's the amount of waste is so much as in the tailings that it will never become saturated. Even if you're really efficient with aeration with supersaturated CO2 layer.
I think if you're looking at that labile reactive components, I think you could achieve nearly complete carbonation of that. Getting into the bulk silicates, that would require more aggressive approaches. So it's a balance between what you can do easily and cheaply versus how much you could sequester CO2.
Other questions? I have one. the stability, you referred to the the product, the magnesium carbonate product that's nice and stable. Under what pH regime and other potentially variable atmospheric conditions is it stable? Like how broad are these standards? There's no point sequestering it if it's not somehow later turns out to be, I don't know, soluble in acid rain or whatever comes next.
I think in this case you're getting in situ carbonation. With these alkaline talions, the pH can be 9 or even above. So if you're in that space,
yeah,
you're quite safe.
Nothing else? Let's thank our speaker one more time. Our next presenter is Pablo Bustos. All right.
I thought it was
Our speaker's getting set up. I will be presenting on using tolerant native plant species as a cost-effective technology to mitigate contaminant dispersion and reduce environmental health risks. As long as that's still there. Thank you.
Buenos días, mi presentación es sobre el potencial de fitoestabilización de plantas nativas. Mi nombre es Pablo Bustos y ahí están mis coautores. Voy a hacer esta presentación en español, pero si necesitara ayuda de traducción, la pegaría ahí. A modo de presentación, comentarles de que yo trabajo en el SMAS Chile, un centro de excelencia internacional de la Universidad de Queensland, el cual entrega soluciones basadas en el conocimiento para los desafíos de la industria minera. Nuestro equipo de trabajo, que es un equipo diverso, con profesionales de diferentes áreas, y donde yo justo no aparezco en las fotos, porque estaba de vacaciones. Bueno, nosotros tenemos 4 equipos de desarrollo: el equipo de procesamiento de energía, agua y emisiones, el equipo de desarrollo social y gobernanza de los recursos, la línea de seguridad integral y salud de las personas, y el equipo donde yo trabajo, que es el equipo de rehabilitación ambiental y dinámicas ecosistémicas. Nosotros trabajamos de forma combinada en diferentes programas de desarrollo, entre los cuales se encuentran relaves y desechos mineros, cierre sostenible de minas, material particulado, cambio climático, minería artesanal y a pequeña escala y salarios sustentables. Ahora, muy bien, a modo de introducción y iniciamos mostrando esta imagen que corresponde al área del estudio, podemos comentar que en el norte de Chile existen una gran cantidad de sitios, en este caso de cuencas, que han sido impactadas durante mucho tiempo por la actividad minera, ya sea por el tiempo extendido en el que se encuentran estas actividades o por eventos puntuales de contaminación, como pueden ser diferentes derrames. En estas diferentes cuencas existen una gran variedad de comunidades vegetacionales que han podido soportar y han crecido y subsistido bajo estas condiciones adversas. Y por lo tanto, estas especies, que son especies nativas, que crecen naturalmente en nuestro país y que no necesitan ayuda del ser humano para poder desarrollarse, representan una oportunidad muy buena para poder desarrollar y estudiar sobre técnicas no convencionales para el manejo de sitios contaminados, como lo puede ser la fitorremediación. En esta imagen se pueden ver las diferentes herramientas dentro de las cuales se encuentra la fitorremediación, y el día de hoy yo me voy a enfocar específicamente en lo que es la fitoestabilización, que es cuando el contaminante queda retenido en la parte radical, en la parte de las raíces de la planta. Ahora bien, el objetivo de este trabajo es evaluar la capacidad que tienen de retener estos contaminantes plantas nativas chilenas y 4 especies, que son Disticlia espicata, Puncus acutus, Chonoplectus americanos y Tesalia absintoides, con especial énfasis en los elementos arsénico, cobre y molibdeno. Aquí se puede ver una imagen que mostré anteriormente que representa el área de estudio. Aquí se puede ver que representa un ecosistema de fondo de quebrada, donde se puede ver un curso de agua y una gran cantidad de especies nativas que desarrollan en conjunto con este suministro hídrico. Dentro de estas especies se encuentran Stiglitz plicata, de la familia de las poáceas, Chonoplectus americanos, de la familia de las ciperáceas, Juncus acutus, que es la que está aquí, que corresponde a la familia de las juncáceas, y por último, Tesalia absintoides, de la familia de las asteráceas. Ahora, en lo que se refiere a la metodología y la toma de muestras y análisis, lo primero que se hizo fue obtener muestras del sustrato, de suelo y sedimentos, y de aguas, para poder así después determinar sus diferentes características físico-químicas. En cuanto a las plantas, se tomaron cuatro individuos de cada una de las especies, los cuales fueron separados en partes aéreas y la raíz. Posteriormente, las muestras de suelo y agua fueron analizadas usando espectrofotometría para los diferentes elementos, y el material vegetal, específicamente el tejido vegetal, fue sometido a un ataque ácido, con una digestión ácida, perdón, y fue sometido también nuevamente a determinación por espectrofotometría. Y por último, ya con los datos de la concentración de elementos en las diferentes partes del tejido vegetal, se determinó el factor de translocación, perdón, que es la concentración del elemento en la parte aérea versus la concentración en las raíces. Ahora, ya entrando a los resultados y también mostrándole un poco el ambiente en el que se encuentra la zona de estudio, podemos ver una de las principales características, que es, por un lado, la alta presencia de sales, como se puede ver traducido en estas costas salinas, y también la presencia de animales, en este caso ganado de comunidades que allí viven. En esta slide lo que se puede ver son los resultados de la caracterización inicial que se hicieron del sustrato, de los suelos y sedimentos, con sus diferentes parámetros, y los resultados de agua también con sus diferentes parámetros. En este caso, primero que me gustaría partir por el arsénico, y también me gustaría destacar de que, por ejemplo, en nuestro país no existe actualmente una ley que establezca límites de salud para el ecosistema en cuanto a los diferentes elementos que pudieran llegar a ser contaminantes. Pues en este caso lo que nosotros hicimos para este trabajo fue basarnos en bibliografía internacional y utilizar las directrices internacionales, específicamente la canadiense y la australiana y de Nueva Zelanda. En este caso podemos ver que el arsénico está por sobre el nivel alto, por lo cual esto se traduce en que se esperan condiciones en las que sobre todo la biota acuática se ve afectada en un porcentaje muy alto. Misma situación ocurre con el cobre, que en este caso la concentración excede ampliamente a las directrices internacionales, y en el caso del molibdeno se puede ver que si bien está muy cercano al rango bajo, lo que implicaría que la posibilidad de encontrar condiciones adversas para la fauna marina, la fauna acuática, serían relativamente bajas. Y en lo que se refiere a la conductividad eléctrica, el pH y el carbono total, estos se correlacionan un poco con el sitio en el que lo encontramos, con niveles de alta salinidad, alta concentración de sales y minerales, y por supuesto también una comunidad vegetacional de vega, donde también es posible encontrar niveles relativamente altos de carbono, muy altos para lo que se considera dentro de la zona en general. Pasando en este caso al agua, ocurre una situación similar. En Chile no existe una legislación que indique niveles máximos o mínimos para la afectación al ecosistema, pero sí existen niveles establecidos para aguas de diferentes usos. En este caso nosotros tomamos como referencia la norma chilena 3333, que lo que hace es ver los límites máximos para la calidad de agua con uso de riego. En este caso podemos ver que, si bien supera la norma de riego en nuestro país, está por bajo el límite establecido por la normativa internacional. En el caso del cobre podemos ver que está bajo de ambos directrices, y en el caso del molibdeno está bajo, lo que podría implicar efectos adversos para la biota acuática, pero está por sobre la norma de riego, aunque se entiende también un poco por la zona en la que nos encontramos, y por lo mismo se encuentran estos valores de conductividad eléctrica y bueno, de un pH moderadamente alcalino. Ahora, yéndonos a los resultados de las especies como tal, del análisis elemental de los tejidos vegetales, se ven en estas diferentes gráficas, donde en esta se ve la concentración en miligramos por kilogramo, en lo que es el sector verde sería la parte aérea y el sector naranja sería las raíces. Versus este gráfico en el que se entregan resultados similares, pero en porcentaje. Esto se hace más que nada para poder determinar posteriormente lo que es el factor de translocación. Aquí el primer resultado que salta a la vista es la alta capacidad de contener arsénico de la especie Chenophractus americanus, esto incluso a pesar de su alta variabilidad, de su error estándar. Un punto importante que quisimos destacar es que basándonos también en bibliografía pudimos ver de que la mayoría de las plantas se encuentran más cercanas a lo que es el rango de suficiente normal para el arsénico, y que solamente en este caso la Diasticlis espicata está dentro de lo que se podría considerar como un rango excesivo tóxico, aunque se encuentra afortunadamente en el límite inferior. Por otro lado, viendo los porcentajes, podemos darnos cuenta de que estas especies tienden a acumular el arsénico más en mayor concentración en las raíces versus la parte aérea, y por tanto nos entrega un FT que es menor a 1, y por tanto estas plantas serían como, en teoría, unos buenos prospectos para la fitoestabilización, ya que tendrían a retener este elemento en las raíces. Este es el cobre, y podemos ver que hay una tendencia un poco similar a lo que es el caso del arsénico, donde la mayoría de las especies se encuentran con niveles que son suficientes normales, salvo Chenophractus americanus, que se encuentra dentro del rango de excesivo tóxico, para lo que el cobre en parte aérea. Y a lo que son los porcentajes, también un resultado relativamente similar al arsénico, donde se puede ver que la mayor concentración se distribuye en las raíces y que muy poco está alocado en la parte aérea. Y por tanto entregaría un FT menor a 1, y por tanto también serían prospectos positivos o deseables para la fitoestabilización. Por último, tenemos el molibdeno, que en este caso la tendencia es la misma, aunque en este caso se puede ver que hay un poco más de translocación a la parte aérea. Y aquí resulta particularmente importante la concentración del elemento en la parte aérea, ya que siendo un sitio que es visitado por ganaderos, donde también hay animales salvajes y animales silvestres, es importante que este rango no esté por sobre los 5 miligramos por kilogramo, porque en este caso podría implicar un riesgo de molibdenosis, que sería una intoxicación por molibdeno y también una competencia con el cobre en el caso de la fisiología de estas especies, que principalmente son rumiantes. Por otro lado, también podemos ver de que, si bien no está marcado como los otros elementos, sí la mayor concentración se ve retenida en las raíces, y una parte menor es trasladada o traslocada a la parte aérea. Por lo tanto, también nos entregaría factores de translocación menores a 1. Ahora bien, si bien nosotros la parte un poco más elemental de los resultados, también al momento de nosotros seleccionar plantas para poder elegirlas como unos buenos candidatos para estas herramientas, tenemos que fijarnos en otras características, como por ejemplo puede ser la generación de cobertura, la resistencia a la salinidad, la generación de biomasa de raíces, la resistencia a la sequía y una rápida propagación. Haciendo un análisis con la bibliografía que nosotros pudimos obtener, hicimos esta pequeña matriz para poder determinar cuáles eran los mejores candidatos, y nos dimos cuenta que Tesserae absinthoides era la que cumplía todas estas características en una mayor medida. Por lo tanto, para nosotros, y considerando como el amplio rango de sitios con impacto minero que hay en el norte de Chile, podría ser uno de los mejores prospectos. Aquí se puede ver un detalle de la especie, y también, por ejemplo, aquí lo podemos ver en una fotografía que de hecho es el área de estudio, y podemos ver ahí cómo se forman tipo matorral, también muy cercano a la zona que está más impactada. Y por último, en las conclusiones, es importante remarcar que si bien no se hicieron análisis fisiológicos de la planta, y que estos son resultados parciales, no se descarta a priori en un futuro a poder realizar esta clase de análisis para poder determinar por qué estas especies son capaces y qué herramientas fisiológicas se ven como comprometidas para poder tener este gran soporte a esta cantidad de concentración de elementos que pueden ser perjudiciales. Lo otro que también resulta bastante interesante, que todas estas especies fueron capaces de retener estos elementos en las raíces, lo cual es muy positivo si es que lo que se aspira es la fitoestabilización, también que la característica de plantas nativas que crecen naturalmente en estos sitios sin la intervención humana también les da un plus a la hora de poder seleccionarlas como candidatos para esta herramienta no tradicional. Y algo que yo personalmente considero muy necesario es que esta clase de estudio igual nos ayuda a generar diferentes instancias para poder llegar en un futuro cercano a establecer guiamientos y directrices nacionales para determinar límites y mínimos para el cuidado de la biota acuática y de los ecosistemas en general. Y por último, si bien este ensayo son una suerte de resultados más acotados, de un ensayo mucho más grande, igual es necesario seguir estudiando estas especies, en qué condiciones se pueden desarrollar y, como dije anteriormente, los mecanismos fisiológicos que se ven implicados en la tolerancia de a estos elementos. Eso, muchas gracias.
Thank you very much. Are there any questions for Bob?
Yeah, I apologize if you actually spoke to this in your talk, but the Tessaria species, is there any opportunity to actually harvest that and ultimately reclaim metals that may be sequestered? In other words, what we sometimes call agro-mining or phyto-mining.
Citas una...
Sí,
está bien.
no.
Por favor, hay una oportunidad para, no sé, harvest.
Cosechar.
Sí. Tessaria para remover cobre y otros elementos de la región.
Sí, es posible. De hecho, yo no participé directamente, pero vi algún estudio para la obtención de nanopartículas de cobre utilizando la estrategia de fitoextracción. Y claro, es cuando el elemento está alocado a la bacteria y después se cosecha y mediante un proceso se pueden obtener estas nanopartículas de cobre.
¿Es un parte de su proyecto o no?
No, pero también lo encuentro muy interesante también por el valor que tiene estas nanopartículas. Y se utilizan también mucho en salud, entonces pueden llegar a ser muy prácticos.
Any other question?
Doug stole my question.
Yeah, he stole mine.
You mentioned arsenic, copper, and moly. Did you analyze other elements?
¿Qué otro elemento?
Hice los análisis de los otros elementos.
Sí, una primera fase es un scoping con los diferentes elementos. Y bueno, esto era lo único que destacaban y que estaba muy por sobre el promedio. Entonces, solamente como para enfocar un poco más la entrega de resultados, mostramos estos elementos, pero también se le mostraron muchos elementos más, mercurio, que también eran de nuestro interés, por ejemplo.
Go ahead.
Okay. Yeah. Well, I was involved in the work, so I can reply as well. So we did a screening of all elements, but these three were the elements that were of more or highest interest considering the contamination pollution in the area and the materials that polluted the area. So we focus on arsenic and molybdenum. That is.
But you did just a screening, so there might be some element that...
Yeah, we analyzed cadmium, mercury, and so on, but we focus on that because we found alarming concentrations of these elements there. So, and of course, because of the molybdenosis, the risk for the ruminants in terms of intoxication of the cattle that are wild cattle, and also, of course, cattle that from the communities. So there are some reports that there is some risk for that. So we were interested because on the reason of these elements, especially molybdenum.
Pensé que puede ser estoy confundido, pero puede ser las concentraciones de cobre son muy similares del rango tóxicos en los raíces.
Sí, lo que pasa es que el rango tóxico que teníamos, en la bibliografía que nosotros descubrimos, era enfocada principalmente en la parte aérea. Había pocos estudios sobre rangos tóxicos para raíces. Lo que nosotros hicimos fue compararlos con otros estudios de la misma especie o de especies de la misma familia en sitios también contaminados por minería, o impactados en este caso. Claro, y ahí el rango era muy amplio, desde mucho menos hasta 10 veces más.
All right, well, please join me in thanking the speaker one more time.
And our next speaker will be Felipe Arcos, who will describe an approach involving addition of polyacrylamide surfactant to permit the recirculation of water in mineral processing plants.
Hola, muy buenas tardes a todos. En primer lugar me disculpo porque mi presentación también será en español y porque mi voz no está del todo bien. La temática que yo voy a presentar hoy día está un poco más relacionada al procesamiento de minerales directamente con un aporte medioambiental que tiene que ver con la buena gestión del agua en el procesamiento de minerales. Yo soy parte de la Universidad de Concepción, del Departamento de Ingeniería Metalúrgica, soy estudiante de doctorado allí y este trabajo se hizo con el apoyo del Centro de Recursos Hídricos para la Agricultura y la Minería y del Departamento de Minas de la Universidad de Talca. La estructura de la presentación incluye una breve introducción asociada a la temática de esta investigación, seguida de los objetivos y la metodología experimental que se utilizaron, para finalmente presentar los resultados y las conclusiones que se obtuvieron aquí. A modo de introducción, entonces, me gustaría comenzar contándole un poco sobre el procesamiento de los minerales de cobre en Chile, especialmente de los minerales sulfurados de cobre. El procesamiento comienza con la extracción del mineral desde la mina, en este caso se ejemplifica con una mina a rajo abierto, ¿cierto? Seguido de esto viene todo el proceso de transporte, de carguío y del primer trancado en seco para posteriormente llegar a la molienda en húmedo. En Chile se utilizan circuitos cerrados de molienda SAC asociada a molienda de bola y a clasificadores de tipo hidrociclones para finalmente, cuando se cumple con los requerimientos granulométricos, pasar a la flotación. En primera etapa se realiza una flotación colectiva donde se obtiene un concentrado de cobre y de molibdeno, y finalmente una flotación selectiva donde se separan dos concentrados, uno con el cobre y otro rico en molibdeno. Entonces, donde nosotros nos centraremos en esta investigación es en la flotación como tal. El proceso de flotación es un proceso de concentración de minerales, de los más utilizados actualmente en la minería del cobre en Chile y en muchas otras minerías a nivel mundial. Consiste básicamente en adherir de manera selectiva estas partículas de mineral de cobre a las burbujas de gas para que puedan ascender a través de la pulpa hacia la parte superior de esta máquina de flotación o celda de flotación y sean recolectadas en el concentrado. El proceso de flotación depende de muchas variables, entre ellas variables que tiene el mineral en la alimentación, como su tamaño de partículas, su liberación y distintos aspectos geometalúrgicos, y también de otras variables que están más asociadas al proceso como tal, como el pH, la densidad de la pulpa, el flujo de aire para que puedan ascender las burbujas hacia la parte superior, el medio acuoso utilizado, y aquí es donde tiene la importancia esta investigación, y también los reactivos de flotación, que son muy importantes tanto en este proceso como en la línea completa de procesamiento de minerales. Los reactivos de flotación se pueden clasificar en tres grandes familias. La primera de ellas se denomina colectores y se podría decir que son de los más importantes para que el proceso se lleve a cabo, ya que son quienes se encargan de entregar un recubrimiento hidrofóbico a estas partículas de mineral valioso para que puedan ser adheridas a las burbujas y recolectadas en el concentrado. Luego tenemos los reactivos que se conocen como espumantes, que están más, que se encargan principalmente de modificar las condiciones del medio acuoso, de disminuir la tensión superficial, de inhibir la coalescencia de estas burbujas para que puedan ascender en las celdas, y finalmente los modificadores, que son una serie de reactivos que se encargan de adecuar las características físico-químicas de las fases involucradas en el proceso para que se lleve a cabo de buena manera. Los principales desafíos que hay actualmente en el procesamiento de minerales: por un lado tenemos la disminución progresiva de las leyes de cobre, en este caso a través del tiempo. Hoy en día en Chile estamos trabajando con leyes de aproximadamente 0,6 a 0,7%, y por otro lado, tenemos un problema de escasez hídrico que se vive actualmente a nivel mundial y que ha sido una de las temáticas fundamentales de este workshop, ¿cierto? Y que en la figura se indica y se puede ver claramente que en la zona norte de Chile, que es donde se concentra la principal actividad minera, es donde existe la mayor escasez de este recurso. Es decir, la demanda supera ampliamente la oferta de agua disponible. Ambos desafíos están conectados directamente, ya que la disminución en las leyes de alimentación de cobre hace que tengamos que procesar una mayor cantidad de mineral para obtener una misma tonelada de cobre fino, y por eso también se debe ocupar una mayor cantidad de agua. Como alternativas para enfrentar estas problemáticas, tenemos por un lado la utilización de agua de mar, que en Chile ya es una de las alternativas de las realidades que se viven actualmente, ya sea utilizada directamente en algunas faenas o en otros lados desalinizadas, y que de acuerdo a las proyecciones de la Comisión Chilena del Cobre, se espera que a fines de esta década la utilización de agua de mar sea de aproximadamente el 70%. Por otro lado, también en las plantas concentradoras se realiza lo que se denomina recirculación de agua, que más adelante se va a explicar un poquito más en detalle, y que en los últimos años ha alcanzado aproximadamente el 75% del total de agua que se agrega al proceso, un 75% entonces es recirculable. Sin embargo, esta alternativa, estas soluciones que se pueden ofrecer para estos desafíos en el procesamiento de minerales no son del todo buenas, ya que la calidad de esta agua puede no ser la misma en comparación a un agua fresca, ¿cierto? ¿Por qué? Porque en el agua de mar tenemos una alta concentración de sales, y en el agua recirculada tenemos también presencia muchas veces de finos y también de reactivos residuales. Como les dije anteriormente, la recirculación de agua se inicia principalmente en estos equipos que se denominan espesadores, que es donde pasan tanto los concentrados como los relaves de flotación, y la idea acá es que las partículas sólidas sedimenten para poder recuperar agua en la parte superior del equipo. Para acelerar este proceso, que muchas veces se lleva a cabo de manera muy lenta debido al tamaño de las partículas involucradas en el sistema, se utilizan reactivos denominados floculantes, que son polímeros de alto peso molecular, como se puede ver acá en la figura, que se encargan de generar agregados, aglomerados de partículas finas para que éstas puedan sedimentar de manera más rápida. Y muchas veces estos reactivos son los que tienen presencia residual en el agua que es recirculada al proceso. De esta manera entonces se plantearon los siguientes objetivos en esta investigación, que fue estudiar el efecto generado por la presencia residual de un floculante, específicamente de una poliacrilamida aniónica, que es de los floculantes que más se utilizan en la minería del cobre en Chile, sobre la flotación de calcopirita bajo distintas condiciones físico-químicas. Para eso, en primer lugar, realizamos un estudio de la flotabilidad de la calcopirita en presencia de este floculante a distintas concentraciones, a distintos pHs y en distintos medios acuosos, ¿cierto? Y posteriormente se estudiaron las interacciones que existían en estos mediante pruebas de absorción del floculante sobre las partículas de calcopirita, y también con las interacciones electrostáticas, principalmente a través de mediciones de potencial Z. Entonces, la metodología experimental, como muestra de reactivos, se utilizó una muestra de calcopirita pura obtenida desde Ward Science, ¿cierto? Como colectores de flotación se utilizó santato amílico de potasio, purificado con el método de recristalización. Como espumante se utilizó el metilisobutilcarbinol, conocido como MIBC, modificadores principalmente para ajustar el pH, el ácido clorhídrico y el hidróxido de sodio. Se utilizaron dos medios acuosos, un agua fresca, como la denominamos en la investigación, que fue una solución 0,01 molar de cloruro de potasio, y agua de mar obtenida de la costa de la región del Biobío, específicamente de Lenga. Como floculante se utilizó este SNF 2350, que corresponde a una poliacrilamida aniónica, que está compuesta principalmente por grupos de acrilamida y por grupos carboxílicos en su estructura. El procedimiento experimental consistió en una combinación manual y en una concentración magnética de la muestra de calcopirita para posteriormente guardarla en bolsas selladas y al vacío con nitrógeno para evitar cualquier tipo de oxidación. Luego se realizaron procesos de molienda, de caracterización en primera instancia y finalmente se realizaron las pruebas experimentales que consistieron básicamente en pruebas de microflotación en esta celda de laboratorio de tipo Patrick Smith, ¿cierto? Con nitrógeno nuevamente para controlar estas condiciones de oxidación en el proceso. Además también se realizaron estas pruebas de absorción en un analizador de carbono orgánico total y las mediciones de potencial Z en un equipo basado en el método de electroforesis. Como resultados, en primera instancia se presentan los resultados obtenidos en agua fresca, ¿cierto? La figura que estoy apuntando, tenemos la recuperación de calcopirita en función del pH y podemos ver que existe una disminución bastante agresiva de la recuperación de la calcopirita a medida que aumenta la concentración del floculante en el proceso. Vemos también que la mayor disminución ocurrió a pH 10, donde pasamos de una recuperación de 96% a una recuperación de 49% cuando había presencia de 10 gramos por tonelada de este floculante en el agua de proceso que simulamos como recirculada. Estos resultados se correlacionan directamente con las pruebas de absorción que hicimos, donde se ve acá que a medida que aumenta el pH, mayor es la interacción y mayor es la absorción del floculante sobre las partículas de calcopirita. Además, presentamos resultados obtenidos de potencial Z, donde se observa que a partir de los valores de pH 6 en adelante, el potencial Z de la calcopirita cambia drásticamente en presencia de 10 gramos por tonelada de este floculante, lo que nos permite inferir que existe interacción entre ambas superficies, aunque todavía no podemos asegurar de qué tipo. Por otro lado, los resultados obtenidos en agua de mar son bastante similares. En el caso de la recuperación de calcopirita, vemos que también existe una relación directa entre la presencia del floculante y los valores de recuperación obtenidos en cada caso, y obviamente se observa que a valores de pH sobre 10 o 10.5 la recuperación de este mineral es bastante disminuye significativamente debido a los precipitados de hidróxido, de calcio y de magnesio que se generan a esos pH en el agua de mar. La mayor disminución se vio a pH 9, donde pasamos de un 79 a un 47% de recuperación de calcopirita. Nuevamente los resultados están muy correlacionados con las pruebas de absorción, donde se ve que a medida que aumenta el pH también aumenta la absorción de estas partículas, de estas moléculas de floculante sobre las partículas de calcopirita. Y finalmente se muestran las gráficas de potencial Z, que como es tan difícil medir en agua de mar debido a la alta concentración de sales que tiene este medio acuoso, se hicieron mediciones en soluciones que contenían sodio, calcio y magnesio. En primer lugar, se aprecia que en ausencia de floculante, los potenciales Z de la calcopirita aumentaron en comparación al caso que vimos en ausencia de sales, ¿cierto? En este caso, entonces, se podría decir que los mismos iones, los cationes presentes en el agua de mar son los que están generando capas de hidratación sobre las partículas de calcopirita y que de esta manera su carga superficial disminuye, ¿cierto? Sigue siendo negativa, pero disminuye. Y por otro lado, cuando se agregó floculante al proceso, en los 3 medios acuosos que se evaluaron, este potencial Z disminuyó. Esto quiere decir que, o lo que podemos inferir a partir de esta gráfica es que debido a la interacción con los cationes presentes en el agua de mar, se dieron distintas interacciones electrostáticas entre las partículas de calcopirita y las moléculas del floculante. De esta manera, entonces, podemos concluir por una parte que la presencia de este floculante en el agua de proceso recirculada tiene un impacto sumamente significativo en la recuperación de calcopirita en ambos tipos de agua evaluados, que esta disminución de la recuperación es directamente proporcional a la concentración del floculante, que además para este floculante en particular, a medida que aumenta el pH, aumenta también la interacción entre las moléculas del floculante y las partículas del mineral. Y finalmente, creemos que esta información, que estos antecedentes son bastante importantes para poder gestionar de mejor manera el agua en el procesamiento de minerales, que es una de las fuentes y de los recursos críticos en nuestra industria en Chile. A modo de futuros estudios, se requiere o se plantea analizar las características físicas y químicas, ver cómo se comporta la molécula del floculante en los distintos medios acuosos, para poder caracterizarlo y realizar comparaciones más precisas, evaluar también el efecto de la degradación mecánica en las moléculas del floculante, ya que como es un reactivo que está sometido a distintas fuerzas de cisalle, cuando es bombeado para ser recirculado aguas arriba, puede ser que sufra degradaciones mecánicas, y estudiar en mayor detalle y por otras técnicas también las interacciones entre las superficies que ya se han comentado. Esa ha sido mi presentación, muchas gracias.
Thank you very much. Any questions for Felipe?
On your second last slide, you had mechanical degradation of flocculent. I'm just curious what that entails.
Do you have a preview of the one before that?
No, it just has mechanical degradation of flocculants.
Oh, okay.
What
Degradación mecánica.
¿Qué me refiero?
¿Qué es?
Como comenté anteriormente, el floculante son moléculas largas, ¿cierto? Pero como son bombeadas dentro de las distintas tuberías, puede que esas moléculas, al ser sometidas a mucha fuerza de cisalle, se degrade y se corten sus moléculas. Entonces, que se degrade esta molécula y que pierda sus características iniciales, que puede perder su alto peso molecular, puede perder sus dimensiones, más que nada.
I understand it's like mechanical, what would you call it?
Digestion.
Anyway, you use a pump to agitate it.
Just agitation.
Yeah.
The functions in different pipes and degrade.
Okay.
Thank you.
And one question. Do you work with a particular size of polyacrylamide?
Yes.
Molecular weights?
Yes. Por eso, como estudio futuro, se plantea esa caracterización a través de la viscosidad intrínseca, del peso molecular, poder caracterizar sin degradación mecánica y con distintas degradaciones mecánicas, y poder relacionar esto también con lo que pase en la bomba, en las tuberías, para tener una comparación directa.
So they use different sizes for comparison.
If there are no other questions, please join me in speaking one more time. Our last speaker for this afternoon is Kyle Reyes from Encuentro University, and he will present the development of solid-state flocculants, also involving polyacrylamides, for the remediation of oil sands tailings.
Right. Thank you, Andrew. So I work in Andrew's lab developing the solid-state flocculant, basically grafting the polyacrylamide onto a petroleum coke-derived activated carbon, just to make sure that there is no polyacrylamide leaching, which hopefully solves your problem, but also just to effectively flocculate mature fine tailings produced by the oil sands industry. So Canada is the third largest oil reserve in the world. And for each barrel of oil they produce about 1.5 barrels of tailings waste. And as of now, it's estimated to produce about, or holds about 1.8 trillion liters of tailings waste. And this basically compromises some process-affected water that rises to the top, containing methanic acids, heavy metals, and polycyclic aromatic hydrocarbons, fluid fine tailings, mature fine tailings, and sand that settles into the bottom. But the main problem that I research on is mature fine tailings. These are have a high solid content of 30 to 35% of negatively charged fine clays that form a stable colloidal suspension that if you leave it to naturally settle by itself, it'll take decades. So currently the oil sands industry uses polyacrylamide to flocculate these mature fine tailings to kind of absorb to the clay particles, bridge them together, form larger aggregates called floc to force them to settle down. So you can collect supernatant water. But the problem with this flocculant, the polyacrylamide, they retain such a high water content, so you don't have a consolidated floc at the bottom, or also you just want more water to remediate out of the floc, out of the mature fine tailings to remediate more water and get the land back. There's also potential leaching of polyacrylamide in treated tailings, as we saw in the previous presentation, and just the cost of using that much polyacrylamide to treat trillions of liters of tailings waste. So what we proposed was to graft the polyacrylamide onto a solid hydrophobic core, such as carbon, just so that the polyacrylamide isn't leached, and again, to reduce the amount of water the flocculant basically absorbs. And we use a surface-initiated atom transfer radical polymerization, and this just basically grows your polymer from the surface of activated carbon, one by one, or per monomer unit, basically. And the advantage of using ATRP is that you can have modular control over your material. You can have a predeterminable molecular weight, so you can have high molecular weights or low. You can have control over the architecture of your material, basically changing the amount of polyacrylamide brushes you can graft on the surface will change the shape of your polymer brush, and you can change the composition of your polymer, basically. So having different functionalities grafted onto your activated carbon. This is the equilibrium of the ATRP process. Basically, you have PX here, which is your initiator, attached onto the activated carbon substrate, your copper catalyst in its reduced form, which forms your radical site where polymerization occurs. And the process basically limits the amount of radical you produce, so you have control over the polymerization process. We graft onto hydroxide activated carbon, which has a very high surface area, upwards of 1,000 meters squared per gram. So you have space to functionalize it while keeping that surface area for potentially more absorption capacity. And you can see its porosity in this SEM image. And then we functionalize it with alkyl halide initiators for the ATRP process to graft the polymer on. So the lab has gotten really good at functionalizing activated carbon. Oliver, my colleague, you should watch his presentation tomorrow. Does most of the work in developing the process of activating petroleum coke to get activated carbon. Then we oxidize it with APS and hydrosulfuric acid to get the hydroxyl group that we can run a esterification reaction to attach the alkyl halide initiator onto the carbon substrate. The group has had initial success grafting the polyacrylamide to activated carbon, getting published in Macromolecular Chemistry and Physics this year. And they basically found that at the same molecular weight of around 200,000 grams per mole of polyacrylamide and the same dose, the polyacrylamide grafted onto activated carbon produced better flocculation results, a clearer supernatant turbidity, and a faster initial settling rate. But this is where I come in. There's still some room for improvement for the ATRP process. Basically, there's some indicators to show if you actually have control over your ATRP process, and it's basically you want a good correlation between your experimental and theoretical molecular weight and the very narrow polydispersity, which is the range of molecular weights you have in your polymer brush. And here in the previous paper, we just have no control over polydispersity, which is high, 2.5, ideally it's 1, and we're reaching lower targeted molecular weights. So the objective of my research has been to optimize the procedure to develop this flocculant, and the indicators again is getting good correlation between experimental and theoretical molecular weight, getting a low polydispersity close to 1, and achieve high monomer conversions. This basically just means that I'm conserving my living halide ends, the X, so that I can grow a larger polymer, and that just gives me more control over the polymerization process. So later on, we can kind of optimize the flocculant by checking different molecular weights, different architectures, there's brushes, mushrooms, and just different compositions by forming block copolymers or alternating copolymers by changing the monomer you feed into the reaction. But the problem with having aqueous ATRP, and you need a water-based ATRP for polyacrylamide, and it's a water-based polymer, is that there's a lot of competing side reactions in the equilibrium. You hydrolyze your initiator, your copper 1 activating catalyst disproportionates in water, and you the halide of your deactivator dissociates. And there's also problems with polyacrylamide itself. The main one being it competitively complexes your deactivator since it has the amide functionality, making it a good ligand for copper, basically. So I've done different reaction conditions, investigated different reaction conditions to try and optimize the process. And I use size exclusion chromatography to measure the molecular weight and polydispersity of my reaction, and Raman spectroscopy to measure the monomer conversion. So first I did, this is the process, the initial process that we used for the first paper, is showing that it reaches a low monomer conversion and reaching lower molecular weights than targeted and a high polydispersity. But if we feed the reducing agent ascorbic acid, we can control the amount of radicals that the polymerization produces, giving us more control, decreasing the polydispersity, and we just can reduce this further to 1.9 by cooling it down to room temperature. Additionally, you can use a co-solvent such as ethanol to decrease the dissociation constant of your halide deactivator, further decreasing the polydispersity, and having halide salts in your reaction to further improve the stability of your deactivator. Additionally, having halide salts and ascorbic acid, which is a reducing agent, this allows you to reduce basically the amount of copper catalyst you have in the reaction solution. And then lastly, we looked at investigating a different halide that can stabilize copper even further. It's a quadridensate ligand. It has a higher activity, so we can reach a higher polymerization at a shorter period of time. And we've replaced all the bromides in the reaction with a less active chloride to reduce the amount of hydrolysis that the initiator experience to limit the termination process. And this produced the best result, reaching 72% conversion, making sure that we're using all the acrylamide as much as possible in a short period of time, 30 minutes, reaching a polydispersity of 1.44, indicating better level of control over the ATRP process. You can see here is my last run, and the previous work the lab has done is that I've narrowed down the dispersity of the molecular weight, reaching a more monodispersed molecular weight at around 200,000 grams per mole. We've also used XPS to kind of characterize the functionality of the flocculant, and we've seen a great increase of nitrogen atomic percent, and that is mainly in the amide form, including that we've actually grafted polyacrylamide onto the activated part. So just a quick conclusion, these are the conditions that we found to control the radical polymerization of polyacrylamide brushes, and these are the conditions that we use to investigate AC-PAN or activated carbon grafted polyacrylamide with higher molecular weights, hoping to reach 10 to the power 6 to 10 to the power 7 grams per mole. And then again, just changing the grafting density for the architecture and make block copolymers or alternating copolymers to kind of tailor the composition to optimize flocculation and even tailor the composition for the remediation of other components, toxic components in tailings waste. I do this research in Kent University, and in this building right here, you can find all the people I'd like to thank, my supervisor, Dr. Andrew Bergenhill, and all my colleagues in the lab. Thank you.
Thank you, Kyle. Are there any questions?
Yes.
Great talk, I really enjoyed it. At the beginning, you mentioned about the high cost of using PAM, so you want to treat all the tailings that are produced. Do you have a sense of how much this process would cost? Is it cost prohibitive, or have you thought about doing a life cycle analysis?
I have not thought about you doing that life cycle impact analysis, but that's definitely, I think would be very valuable, yeah.
Can I follow up that question with
Go ahead.
a question that might prompt you to a different answer, which is how much equivalent polyacrylamide do you currently, or have we sort of demonstrated that we use?
So the AC-PAM that was able to flocculate that only has 10% polyacrylamide, compared which at the same dose flocculated a lot better, that's a lot less polyacrylamide. I don't have to complete.
So right now it's about a factor of 5 reduction in the quantity of polymer. So given the scale they work on, that's pretty good.
And it's also giving a value-added product of their already byproduct of petroleum coal.
Chris, do you think this might have any ancillary benefit on removal of the naphthenic acids?
So that's that is the next part of the research.
Okay.
That's Tegan's project.
That I'm not gonna worry about.
Somebody else, probably.
Yeah.
Yes, excellent question. If there's nothing else, let's thank all the speakers for this afternoon. I would normally invite you back here X number of minutes from now, but I actually have no idea when the next session starts.
About 15 to 20 minutes back.
Okay, so no more than
20 minutes.
No more than 20 minutes. That would make it 4:20.
You do it again for me. He'd be delighted.
Yeah.
Sorry? I don't know who is the chair. The next one, but I'm sure. Okay. Next door. Here.
Yeah.
Yeah. Yeah. Skip design not to work, but you can certainly. Yes.
And do they charge water first and then inject it? Okay.
Things.
Is it a quick injection? Mix it?
Well, it's very, very attractive when it's captured. This was this morning. You don't need this one.
Sorry.
Sure, why not? Isn't that nice? And there's a USB coder.
You're not actually measuring, they're just adding some and they don't have it basically. They don't have to. Yeah, gotcha.
Do you have an idea of why the top of fire flotation decreases?
You can't do it. I can't minimize Zoom.
So when these color surface of very
Exactly.
yes.
Even storms? Yeah, it cools it, and prevents the other agent from being in.
Yeah, okay. I just thought it was supposed to be.
Topic
Yeah, it's for the recording. It's for the transmission. Yeah, sorry.
Okay, so as I was saying,
Yeah.
this transformation that happens in aquatic environment is a critical step towards the accumulation of this toxic heavy metal in the food chain. Oh, no, this is not working.
Just click on this. Yeah. Just click on this. You're fine. Yeah. Yeah, just here.
Yeah.
Where's the button?
Yeah. Okay. So there's many factors that influence the efficiency of this transformation, and in understanding how these factors influence the methylation is extremely important in defining or establishing remediation techniques or the remediation projects in contaminated areas. I have here several different factors. There's many more that I don't represent here, and one of the ones that I studied that I'm going to describe today is wetting cycles. So wetting cycles, they are known to enhance this transformation, the methylation of mercury, and the metal mercury concentrations normally increase in both water, sediment, and fish after a flooding event. The thing is that the influence of wetting cycles highly depends from location to location. So we wanted to see how the wetting cycles influence our specific location. So our location that I'm studying is the Wabigoon River. This is a river located in the northwest Ontario, close to the border to Manitoba. And this river is famous for severe mercury pollution that happened in the 1960s. Caused by chlorine-alkali factory, and even though the pollution from the factory has stopped several decades ago, to this day there is still elevated mercury concentrations in both fauna and flora in this system. So how we did this experiment? We selected two different locations here identified in the river. They are located around 60 kilometers downstream from the pollution source. They represent two different types of ecosystems, a wetland ecosystem and a riverbed or riverbank ecosystem, because we wanted to see how these two different ecosystems would react to the wetting cycles. These locations were identified with previous results from the PhD to be producers, to be hotspots for metal mercury producers. So we wanted to see how these wetting cycles would influence and see if potentially reducing the water levels in the river could be a good remediation to reduce methylation production, metal mercury production in this system. And so in all of these locations, we collected sediment cores from dry areas. So these are sediment cores around 50 meters away from the water level, and are locations that will be submerged in water once the water level rises. These cores were separated in the top layer, the 3 centimeters, and the bottom layer, 3 centimeters. In order to identify where the methylation is predominant, if there is any difference between the both layers. And then these cores were also divided in 3 different treatments. We have a control treatment where nothing was added, there was no disturbance. A non-spiked treatment that was wetted using river water at time 0. And then at day 6 to represent a second wetting cycle, so repeatability of wetting cycles. And then finally a spiked sample that was wetted at the same time 0 and day 6, where here we added an enriched isotope tracer in order to follow the methylation of mercury into methylmercury from the added spike. All of these different treatments were subsampled at time 0, 1 hour, 24 hours, 3 days, 6 days, and then at day 6 they were re-wetted and collected immediately after and 1 hour after the second wetting cycle. And all of these were measured for total mercury and methylmercury concentrations using the ICP-MS. So here on the results, I'm showing the water content for both dry and wet samples. This is important because, as you can see, our dry samples didn't start from a complete dryness. They actually start around 28%, while the wet samples, they were wetted to around 45%. All of the dry and wet samples went through a similar drying process, air drying for 6 days, resulting around 4% of water at the end of the 6th day. And then, as you can see, the wet samples were re-wetted again to around 45% in the second wetting cycle. So here first we looked at ambient concentrations to follow the methylation, to see if methylation is happening. As you can see here, there is not a lot of difference between the wet and the dry samples. So we hypothesized that because they follow the same drying process, even though they were initially at different water contents, we hypothesized that the drying process is a determining factor in this wetting and drying experiments. Another thing that we can see here, so in the top we have the riverbed location, at the bottom we have the wetland location, and we can see they have very different concentrations of methylmercury, with the riverbed location having higher concentrations. So in order to better compare the two locations and try to understand if there is a location that is producing more methylmercury after the flooding event, we decided to normalize methylmercury using total mercury concentrations. So then we have the percent mercury, which is a proportion of mercury, how much methylmercury is in the methylmercury form compared to the total mercury. What is the proportion of methylmercury to the total mercury concentration in these two locations? And now when we do this, again, as we can see, there's still not much difference between the control and the wet samples. And now it's easier to see that, in fact, the riverbed location is producing more methylmercury, has higher methylmercury proportions compared to the wetland location. Finally, this is the spiked sample, and this proves again that the Wabigoon Rapids, so the riverbed location, is producing in fact more. We see here that for the wetland, there is mostly always below 0.6% of the added spike that was transformed into methylmercury, while for the riverbed location, we have transformations of up to 4% of the added spike. So to conclude, the methylmercury levels or production are mainly affected by the drying process, and they are not the extent of the wetting. It's not a determining factor here. Additionally, the flooded riverbank banks are more susceptible to the wetting and drying cycles and can become an area of concern in case of flooding in this system. We hypothesize that this happens maybe due to pre-adaptations of the bacterial communities responsible for the methylation to the moisture conditions present in wetlands, or due to different characterization of organic matter at different ecosystems.
Thank you, Ajay, for this interesting presentation regarding the dangerous metal mercury. So I'm sorry for the disturbance in your presentation. So we have time for questions. So if you want questions,
Is there a reason why you focused on the surface sediments and you split them into the top 3 and then 3 to 6? Was there something you were expecting to be different?
it's for the recording. So.
Okay. Yeah, actually, I was not expecting them to be different because we normally see very consistent ventilation in the top 5 to 6 centimeters of sediments, but we hypothesized that wetting extent doesn't go to deeper sediments, so we could still have slightly different bacteria communities. Yeah. But in fact, there was no statistical difference in the different layers. Thank you. Yeah.
Any more questions? No, I have one. Yes, it's related with you said that there is a increase in the transformation of the ventilation in some of the samples due to the changes in the wet-dry cycle. So my question is, it means or it translates to a change in the humidity of the mercury from the sediments to the water column, or this?
Yeah, that's a very good question indeed. So there is studies that prove that metal mercury concentrations after flooding increase not only due to the enhancement of metallation, but also because metal mercury is absorbing from the sediments. However, our method doesn't measure the pore water or metal mercury in water, so we cannot differentiate if it is being disobserved or produced with our experimental design.
Oh, that's fine. Okay, thank you very much, Edwin. I know how it works.
Through the street.
What? Whoops. Okay.
It's always
Okay. So, yeah, so our final speaker this afternoon is James Watt from the University of Edinburgh. So, he will present a research or presentation entitled Application of Sequential Extractions and X-ray Absorption Spectroscopy to Determine the Expedition of Vanadium Greenland Contaminated Sediment. So, please, James.
Thanks a lot, Clement. Thanks for sticking out to the end of the day. The benefit is we get to the wine quicker. Which is good. So, basically today we're going to be talking about some of my doctoral work that I did in the depths of the pandemic, which was an interesting experience. And basically what I was looking at was the metal vanadium, which is not the most glamorous of potentially toxic elements. Generally, vanadium is found in all coal and oil deposits, and basically its major natural sources are found in soils and rocks. And as you can see, there's a wide variety of minerals that all contain vanadium somewhere within their framework. But the way that these minerals are either mined in industry are never for the actual vanadium themselves. It's often for things that co-occur like uranium or lead in the case of the vanadates, or sometimes even rare earth elements like tellurium. And by this point, it's always just been a co-occurring contaminant. It's never been the primary focus of environmental chemists or environmental scientists. So the problem is that when we use these materials, either the burning of the oil or the coal, the vanadium gets emitted into the atmosphere where it's rained out, which is in just a second, but also it's just concentrated in these industrially relevant wastes, such as red mud, which is the byproduct of aluminium production, steel slags, so from Craig's talk this morning, basic oxygen furnace slags, they're full of vanadium. As I said there, uranium ore processing is another major anthropogenic source. But some of these sources are dwindling, we're phasing out coal and oil, so some people would say, well, it's not really much of an issue, but the thing is that we're now positioned, and what we've been talking a lot about recently, or today, is this idea of transitioning and decarbonising energy. From what we've seen is that, from this graph here from the USGS, you can see that the primary extraction of vanadium has gone through quite an exponential increase for the last, well, since about the 1960s, and that's driven by the fact that we found new technological applications of vanadium. So if we think of the future world and what we're going to need more of, well, aerospace isn't going away anywhere, considering they're changing fuels. Wind turbines will be driving the green transition, partly of energy. Even fusion reactors, that concerted effort to try and find that truly renewable source that's always 30 years away. But the fact is that these are all globally significant technologies that we need to implement, we need to adapt or continue to use in our global society, in our global economic system. So this means there's probably going to be, in the future, more vanadium in wastes, more vanadium being released into the environment. Because when we look at a simplified version of the global vanadium cycle, yes, we have the natural sources in these dashed boxes here, but if we look, even within natural sources, we know that environmental change is going to be driving more forest fires, it's going to be taking more vanadium from the soil into the atmosphere, the outer will be rained out into our freshwater systems. Equally, those industrial sources as well, either through accidental releases from tailings failures or just discharges from industry, are going to result in increased concentrations of vanadium entering our freshwater systems. So when we look at the complexation or the environmental geochemical behaviour of vanadium in solution, it's relatively complex, certainly compared to some other metals. The main take-home message is that we have 3 stable oxidation states with vanadium 5, 4, and 3. We also see there's a range of charges, which also makes the job of speciation a bit more difficult. We're not just dealing with just cations, there's a mixture of anions and cations. And as with a lot of transition metals, speciation is key for dictating toxicity, and it's quite profound in the sense of vanadium. And that vanadium 5 is known now to be carcinogenic. It can cross the placental barrier and impact offspring of both humans and animals. For contrast, vanadium 4 is actually used as an insulin replacement therapy. So it's actually medicinal in that sense. So obviously very subtle changes in speciation, profound differences in their ecotoxicological effects. The problem is, that's the aquatic systems, those are solutions in labs. A lot of the time we're talking about solid phases containing vanadium. These are the sources, these are big parts of environmental systems. We don't really know anything about it. The reason we know very little about solid phase speciation is because it's hard to get to it. As soon as you dissolve that solid phase, you're probably going to be changing the speciation of what it was originally, and then what are you looking at? Is it real? So, with that, what I set out to do was I was going to try and basically use a central example of just introduce in just a second, but I wanted to try and understand what are the dominant fractions of vanadium within industrially contaminated sediments. And once we find out those fractions, what is the speciation within those fractions? Because if the fraction is going to turn over or change with seasonal change or future environmental change, we should probably know what is it, vanadium 4 or vanadium 5 or even vanadium 3. And basically I wanted to compare the 2 methods I used to try and understand whether we get agreement, because it's always kind of the basis of method development. So I was fortunate enough that I'm from Edinburgh, and just in my back garden there's a horribly contaminated lake. So this is Fife and a place called Kinghorn, and there's a large red mud repository that was basically associated to an aluminium plant that used to make hurricane fighter aircraft in the Second World War. And the plan was, if you look at the contours, this is a hill, this is the top of the hill, and they poured all the red mud into the top of the hill, and they didn't line the pit. And unfortunately, there's actually a small burn here that feeds this water body here, which is Kinghorn Loch. So, from about 1950 until the 1980s, what we see is that discharges of red mud, which is highly caustic, it's a pH of 14, we can see that the mean pH of Kinghorn Loch slowly starts drifting up to a point where it got to a maximum pH of 11.6. So great for making your hands soft, but not great if you're a fish or anything else. Fortunately, in the 1980s, there was a period of restoration. They diverted the leachate away through to a settling pond and a treatment plan using seawater, and so you saw dramatic decreases in the amount of red mud entering the lake. And since then, it took about 7 years for the lake to enter this new stable regime. It never returned to the sort of low levels here. Its mean pH now is about 9, and sometimes during particularly active summers where there's lots of algal production, we can get as high as almost 10. So it makes an excellent sort of sentinel or case study to look at what happens to aquatic systems when they become contaminated with vanadium-rich wastes. So during the process of, I take a lot of different cores, but what I'll be presenting today are these 3 cores in purple. And basically they represent samples from where the leachate came in primarily during that period of contamination. There is also a northern inlet that just comes through some farmlands, and its mass balance is shown that basically has very little vanadium contribution at all, so we can kind of ignore it. And then the deepest point is a kettle bowl lake, which is a single deep point here. So I thought that would be an interesting place to look at whether that long-term speciation was different from where the waste came. 2 cores, chopped them up into 2 centimetre sections. Kept it in a glove box because the sediment is highly reducing, basically all the way from the sediment-water interface all the way down, highly reducing. So we had to chop it up in a glove box and freeze drying to try and preserve the speciation of the solid phases as best as we could. So, part 1 is sort of traditional sequential extraction procedure, and I use one called the Senna extraction. So the Senna extraction originally was devised for phosphate fractionation in freshwater sediments, and I thought I'd use it because at the time I was doing this work, there was no standardized methods for extracting vanadium to sediments, so no new bothers. The rationale for that was that basically vanadium, phosphorus, arsenic, many other oxyanides, they all have identical electronic configurations or speciation behavior in solution. And basically what the regime is that we go through in sort of typical sequential extraction style where we use a salt solution, so it's ammonium chloride, to take off easily exchangeable vanadium from surfaces of things. We then use a reducing agent, which is sodium dithionite, buffered to a neutral pH, stop the dissolution of acid-sensitive species. We then move on to the organic phase, so 0.1 molar sodium hydroxide, then 1 molar hydrochloric acid is taken out to the carbonates that may be there, and then everything that's left, the residual step, was dissolved up using aqua regia as the most recalcitrant phase, when it's least reactive to the environment. And all these were quantified using either ICP OES, if the concentrations were sufficiently high, or ICP MS. The results of that are this. So basically, we have each core in a band. So this is the leachate inlet, northern inlet, and then the deepest point. And what we can see, and there's basically very little variation, or almost like random variation, that top 30 centimeters of the core. And what we see is that there's a similar pattern emerging. It doesn't really matter where you are in Kinghorn Loch. Vanadium is mainly distributed between organic matter and carbonate, and the carbonate was particularly surprising because there really wasn't very much indication that would be the case at all from the literature. The association with reducible metal phases, such as iron and manganese oxide hydroxides, is well known, as is the organic matter. So this was an interesting place to start, especially this carbonate phase. So we had to dig in a little bit deeper because I didn't quite understand what the relationship was between carbonates and vanadium. So what I did was I synthesized some calcium carbonate, and what I did was I then either coated just the outside of the carbonate with vanadium, or during the synthesis I incorporated vanadium, so in an attempt to try and get it incorporated within the mineral structure. So this graph here on the right hand side is basically a test of trying to show that whether it was a phosphate buffer where sodium hydroxide was able to effectively remove all the vanadium from outside the particle. So comparing it to a total digest of hydrochloric acid, we found that yes, basically, we could remove all the vanadium from the outside of the particle. And then when we took to synthesizing calcium carbonate with different concentrations of vanadium during the point where the crystals were forming, what we find is that most of the vanadium is stuck on the outside. That's represented by the either the phosphate buffer in orange or the sodium hydroxide in green. But what we find is the difference, there's always vanadium that has actually been incorporated inside calcium carbonate. And this is very surprising, because for those that know, calcium carbonate is a trigonal planar. That's where the carbonate ions are. And as I said before, vanadium is a tetrahedron, so it shouldn't really fit. So again, I have to probe further. Is it real? Doing some high resolution XRD, what I found was that running multiple scans, we found this black line here is pure control, so there's no vanadium in it at all, and that's pure calcium carbonate. The blue line here is calcite that's been doped with vanadium internally. What we found is that the crystal structure has shifted, and basically when we've done a rank balance analysis, we see that there is a significant difference in the X parameters. So if we consider the error on the two different forms, we find that they are significantly different from each other, but there's been no difference in the Y direction. So basically the crystals haven't gone up like this, they've bulged outwards, almost rounded out. So this was again very surprising because we haven't seen this before. So at that point we kind of run out of options for sequential extractions, because that's the limit of resolution you're going to get. It's just concentration based, and maybe if you get a trace in an XRD. So what I did then was I thought, let's go to a synchrotron, let's use ultra high resolution speciation methods to see if we get the same agreement. So this process is where you get your sediment that you've preserved, you mill it up into a powder, you press it into a very, very small disc, there's often around 13 millimeters across, and then you take it to a synchrotron. And the idea is that you're meant to synthesize lots of different sort of standards of what you think the vanadium is going to be contained in the sediment. So using sequential extraction, I knew that there was chemical substances, I knew that organic matter probably played a role, I knew that there were probably ion phases, and again, you have to just go off informed decision, so ferrite graphite's very common within lake sediments. And then ideally, we also used some synthetic oxides that are there to represent different oxidation states. So for example, V2O5, vanadium pentoxide, everything's vanadium in its fifth oxidation state. Everything's in its fourth oxidation state, so on and so forth. So again, we have a pure measure of different oxidation states of vanadium. So the idea is that you then collect individual spectra on the synchrotron, and by measuring different properties of each sample, so maybe the height of the pre-edge peak, or maybe the half inflection of what we call the edge, that's what its dotted line is, we can use them to compute and plot different qualities of these standards, and also natural samples. And that's what I present here. So basically within this plot here, we have just two different parameters of that spectra. There can be various ones, there's no standardized way to look at it. These brown X's are the sediment samples, so those sections I took. And these other symbols here are those standard reference materials I've measured. So if we just look at this left-hand side here, when you relate the centroid energy, so that's the position of the middle of that first peak in the spectra, and then the height of it, what you can tell is the symmetry or the structure of where the vanadium is located. The important thing about this is that, yeah, we find that most of the environmental samples are related very closely to chemical substances that are either bonded with iron or just on their own. But something that was really good to see was that our sample of vanadium incorporated into calcium carbonate has shifted down from a pure tetrahedron. So this is a sample where everything's a tetrahedron, but basically we have a reduced intensity, which means that there's a distortion within the actual molecule, which means it probably is giving us more evidence that yes, that tetrahedron molecule is actually cramming itself into where a trigonal planar site is. and it's causing distortion, and it's therefore subsequently a reduction in the intensity. So then we move over to the speciation, and what we get here is, this is almost like a classic mixing plot, so vanadium 3 standard, vanadium 4, and vanadium 5 base standards. But what we find is that most of our environmental samples sit closer to 4, but they're still up towards the 5 as well. At the synchrotron, it's a 1 millimeter by 1 millimeter beam, so you're actually looking at the average speciation, the average redox environment, so quite a big part of a sample relative to a synchrotron technique. And again, this was really surprising because we took efforts to conserve the speciation. It was a highly reducing sediment, and yet despite being highly reducing, we still have vanadium 4 and 5 being conserved. It's not being reduced. So vanadium will happily be spontaneously reduced in low redox situations. That's the speciation solved, but how do we relate the results to the sequential extraction? We have percentage contributions. Well, what you can do is you can take your standards, you can then blend them together and try and get them to best define a known environmental sample. This is called linear combination fitting. We can give different lines different weightings, and the weightings are what the contributions are. They're relatively comparable to the sequential extraction results from earlier. Quite the difference. So what we see is that, yes, organic matter, iron phases, and calcium carbonate are present. We've got the right phases, but the proportions are dramatically different. They're very, very different. And that's from the top of the core section to the bottom. We can only do very limited samples because synchrotron techniques are a very low throughput technique. But when we look at the fit, so the fit is the red line here. Apologies for it being a bit blurry. Red is basically my combined set of standards, and the blue is the empirical observation from the environmental samples. And what you see is that we actually do get pretty good fit between our limits of analysis, which are these two brown lines. So overall, I think we've done a fairly good example of fitting the major features of these environmental samples, and we're getting between 82 and 94% of the total spectra explained by our model. So as I said, if you compare the two techniques side by side, we're left with a bit of a conundrum, which is, well, which one do we use? And it becomes a bit of a chicken and egg situation where, as I said, you need the sequential extractions to inform you what kind of standards you need to then to run something like a synchrotron experiment. So at this point, we're not really discounting either or, because this is incredibly low throughput. You'll never get the representativity of the environment and that sort of big scale environmental understanding either. So in conclusion, there are ways to look at the solid phase speciation of potentially toxic elements within solid phases from sediments. But really at this point, it's probably a belt and braces approach where you can't just rely on one technique. You have to use different techniques to inform and double check whether things are real. And ultimately the idea is that it's relevant because by identifying those phases, we can then understand whether environmental, and this is postulating, just proving, environmental processes that could be changing anoxia lakes driving reductive dissolution, the transfer of species up into fish and into plants that we've heard so much about over the day are really important processes. And again, they all need to be resolved down at the base level, which is what species is found in your sediment. So thanks for your attention, and I'll happily take questions.
Thank you, James, for this presentation. I got it managed, so we have time for a couple of questions. Yeah. It's for the record.
James, thank you, very interesting. I was like when I get to see a synchrotron in an analytical sort of application. That having been said, what about other X-ray techniques? We do a lot of X-ray photoelectron spectroscopy, for example. Does that not give you sort of more information about the speciation?
I'm not actually too familiar with that technique, so I'd love to actually have a conversation about that specific beamline. The reason we went for linear combination fitting from Zane's was because we had this initial idea that there was probably a very large variety of individual species or fractions within what we would call organic matter. Because again, it completely depends what type of organic matter you have to synthesize and use. But how would that change then from electron photon spectroscopy?
Well, it's a little more surface sensitive, but more binding energy, chemically speciation specific. So you get less coordination dependence in than XANs, but more tabulated chemical speciation. Yeah, so there's a kind of wealth of information that we should talk about.
Definitely.
Do quite a lot.
Yeah, thanks. Yeah.
Any more questions? Yeah. Yeah.
I saw the ratio of the iron, like you had the one layer that had a lot more iron in it. What was that? Is there also a lot more iron in that layer? Or is your...
Yes, so this was example data from the bottom section near the leachate inlet. The main understanding that is that obviously we go back in time, the deeper we go, and that there was, total iron was much higher. And this is the initial collision plume of that red mud. It's called red mud because it's almost percent levels of iron within the leachate itself. So that's what I was interpreting as a legacy signal of the original deposition, particularly high set of years or where they released a lot of the contamination, or rain driving a lot of the leachate. There was a landfill. It's hard to say because we or someone prior to me attempted to do some lead-210 dating to actually get a chronology of, but what they found was that the sediment's also relatively well mixed. So it wasn't at the same point, but they found that there are carp in the lake as well, which can churn up the sediment, ruin things like stick. It's a complicated environment to try and really say, it's definitely because of that. But there was more total iron at that point.
But there's more iron there, so therefore the vanadium is more likely to be...
Yes, it's just a dominant phase. Right. It would be competing with arsenic and phosphorus and other things, but there are more sites there.
But there's still a lot of iron at the top. And I guess, are the speciation, is there a difference between these more iron?
Oh, no, so for using individual samples, also from the fit, we know that vanadium-5 will bind to ferrihydrite and has a monodentate complex, and then things we've got there have a bidentate complex. And it's always vanadium-5 and it's associated with iron phases. So I wasn't too concerned about it being a rogue vanadium-4 on a iron species, an iron phase, if that makes sense.
Oh, just wonder what functional groups you think vanadium is binding to in humic acids?
The humic acids, so it was interesting, so for some of these fits, it was a ternary complex of humic substances, iron, and then the vanadium. So the vanadium, because it's at higher pHs, it will tend to have a negative charge, so the iron's acting as a bridge, so to speak. But in terms of, it is a bit of a puzzle when you're just looking at just humic acids, and it doesn't have a classic cation bridge. What is it sticking to? But humic acid being so complicated. What I can say is, I didn't present it here, is that most of the organic matter in the lake is in lake derived. There's a lot of algal blooms every year because of the phosphate from the red mud as well. So yeah, I need to look at more FTIR studies to nail that. That's a good question.
You mentioned the incorporation into the calcites. Do you know how much was incorporated in calcites, and are the waters saturated in calcites? Are they saturated in other minerals?
Yes, so through modelling, there's basically an abundance of carbonate and calcium. So one thing the northern inlet of the lake actually does provide is calcium. So yes, the saturation indexes are saturated at that point, and so that's why I've postulated this point here. When you're getting neo-formed calcium carbonate, but it's probably just a very slow trickle feed process, because the aqueous concentrations of vanadium in the lake water, maximum sort of 20 to 30 parts per billion. So in my lab experiment, we were finding, using quite high doses, you're getting maybe 26 to 30% of the vanadium being incorporated. So you scale it down. I'm not surprised that in real life, you don't have that. You just have very, very, very little. That's where I'd be more inclined to believe the same foundation.
And do you think the mass balance, if there's enough calcium precipitation to really impact the area?
Yeah, I think so. So work done in the 80s from a PhD that remediated the site. They did a full mass balance of major anions and cations, and there's a
Last question, could you use that as a remediation strategy? Could you attempt to initiate calcium chloride?
Yeah, that's a really good point. So Rio Tinto are the owners of this site, or through Alcam, which is a subsidiary, and they were really interested by this. So they thought, in an engineering context, you can have a nice big calcium carbonate bed and flow your waste through, and you can pick out. So yeah.
Thanks.
Thanks.
Okay, so thank you, James. So we close the session. We have the opportunity to see the relevance of the investigation for different aspects related with geochemistry and also toxicology. So we have now an interesting poster sessions. And I don't know if Margaret, any analysis regarding the poster session, please.
Yeah, so the poster session is outside on the terrace. All the posters are up, so I think there are 8 posters for you to go and look at all of them there too as well. So that will be interesting, given what we just been talking about in the session. And there will also be drinks, so there'll be some nice red wine and some soft drinks for those who'd like them served on the terrace. In terms of the bus, if you're coming back, if you're staying at the Hilton Hotel, the bus leaves at 7 p.m. So I think we need to be at the entrance where we came in. We're going to maybe walk together back to that entrance and get on the bus for 7 p.m. Okay, thank you very much.
Yeah, to make all your own stand.
Massive thing we need to do is introduce too much here on polyatomic. At the point of 20-meter powders. Yeah, and you know, because it's pandemic.
We have to be violent.
Yes. Originally I'm synchronizing.
Okay,